Hello and welcome to Pre-Algebra Lesson 1. In this video, we're going to learn about place value. So the lesson objectives for today, we want to learn basic definitions of terms relating to place value. We want to gain a basic understanding of how our number system works. And additionally, we want to learn how to construct and use a place value chart. All right, let's start out by talking about the whole numbers. So the whole numbers start with 0. So that's your smallest whole number, and then increase in increments of 1 indefinitely. So I've written here the whole numbers, and look how we've listed 0, the smallest whole number, first or in the leftmost position. And then you're going to put a comma. You're going to add 1 to 0 to get to 1. So you put your next largest whole number there, and then you can just keep adding 1. So then you would go to 2, then 3, then 4, then 5. There's not a largest whole number. You can keep just adding 1 to get to the next largest whole number. So what you'd want to do at some point is stop and put your final comma, and then these 3 dots here. And that's just going to tell you that the pattern continues forever. So after 5 comes 6, then 7, then 8, then 9, and so on and so forth. All right, so now let's talk about what we call the digits. These are the first 10 whole numbers, and they are used to build numbers. So I have here the whole numbers, 0 through 9, so the first 10 whole numbers are referred to as digits. So I've listed them out here, so 0 through 9. The whole key is that as we change a digit's position in a number, its value is going to change. So I have here that our number system relies on the digits. So again, that's the first 10 whole numbers, and a place value to build each number. So it doesn't matter how large of a number you have or how small of a number you have, you're only going to use the digits to build that number. The key, again, is just as you change the position or the placement of a digit in a number, its value is going to change. That's why we call our number system a place value system. So to show this, let's take a look at 4 numbers, each containing the digit 9. All right, so what we're going to do is look at the 4 numbers we have here. So 49, 192, 3,945, and then 9,687. There are some things that we're going to do here that we haven't talked about yet. So just take everything as a given, and then I'm going to fully explain as we move forward. So the first thing is I'm going to write each number in what we call expanded notation, and that is going to be covered in the next lesson. It's just a way that we can write a number such that the value of each digit is fully shown. So for example, something like 49, I could write that as 40 plus 9. Or something like 192, I would say that's 100 plus 90 plus 2. Then something like 3,945, that's going to be 3,000 plus 900 plus 40 plus 5. And then 9,687, that's going to be 9,000 plus 600 plus 80 plus 7. So we'll learn how to do this in the next lesson. But right now, let's just take it as a given and use it to understand what's going on. We have a 9 in each number, so that digit 9. So here, 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 and here. Now look at it in the expanded form of each number. So it's going to be here, 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 and then here. Notice that in the first number, 49, it's just a 9. And that's coming from the fact that the 9 is in the ones place there, so its value comes from 9 times 1, which is 9. Then in the next number, you have 192. Well, this 9 is in what we call the tens place, so it's 9 times 10, or 90. Then when we get to 3,945, the 9 is in the hundreds place, so it's 9 times 100, or 900. Then finally, when we get to 9,687, the 9 is in the thousands place, so it's 9 times 1,000, or 9,000. The main thing here is to understand that as we change the position of that 9, that digit in a number, it's getting a different value. So it's getting its value based on where it is in the number, its position, or its placement. Now, as a final example, let's just think about, instead of 49, let's write 94. And let's think about the 9 here. Let me write this out and say that this is 90 plus 4. Well, now this 9 is a 90. It's in the tens place, it's 9 times 10, or 90. Here, the 9 is just a 9. 9 times 1, which is 9. But notice that these numbers are built with the same 2 digits, a 4 and a 9. But this one is 49, which is 40 plus 9, and this is 94, which is 90 plus 4. We know that $94 would be more than $49, so obviously these two numbers are not the same, even though they contain the same 2 digits only. So the position of a digit in a number is going to determine its value. Okay, let's look at what we call a place value chart. So this is a good way to understand how to find the place value for a given digit in a number. So to start off, I'm just going to pick a number a smaller number, let's say something like 1052. And you're just going to feed this into the place value chart. So provided you're working with a whole number, you can just make your own example. If you're working with a decimal, then you're going to need an expanded place value chart. We'll cover that later on in the course. For right now, the rightmost digit of your whole number, in this case it's a 2, and that's going to be in what we call the ones place. I'll talk more about this in a moment, but basically for right now, let's just feed this in to the rightmost position on that place value chart. So that 2 is going to go right there, again, where it says ones. Okay, let me get rid of this highlighting so nobody's lost. As I move to the left in my number, I'm going to match that movement to the left on my place value chart. So this 5 is now going to go here where it says tens. I go to the left. This 0 is now going to go in this position that says hundreds. I'm just going to the left. Then I'm going to go to the left one more time. This 1 is going to go into the thousands. So what does it mean to have ones, tens, hundreds, thousands, all these things? Where does that come from and what does it mean? Well, the first thing is this is all based on 10. Once you understand that, it becomes very easy to come up with these names. So I'm just going to start. You see that this says ones here. I'm just going to write a 1. Then as I move to the left, let me just write a 10, let me write 100, and let me write 1000, and I'm just going to stop there, and I'm going to show you the pattern. So basically what's happening is, as I move to the left, I'm just multiplying by 10. So 1 times 10 gives me 10. Then as I move to the left, I'm multiplying by 10. 10 times 10 gives me 100. As I move to the left, I'm just multiplying by 10. So 100 times 10 gives me 1,000. This would continue forever and ever and ever as you move to the left. Now, it's also true as you move to the right, you're dividing by 10. We can show that real quick too. So if I took 1,000 and I divide by 10, I get 100. If I take 100 and I divide by 10, I get 10. If I take 10 and I divide by 10, I'm going to get 1. So we see the pattern. As we move to the left, we multiply by 10. As we go to the right, we divide by 10. So we can use that to come up with these names. Just remember that the rightmost position here is the ones place. You can just think about that as a 1. That's all you have to remember. Then as you move to the left, well, hey, I multiply by 10, so I have a 10. Well, now I say tens. Move to the left, multiply by 10, I get 100, so we say hundreds, and this just continues. So then you'd have thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillions. You just keep multiplying by 10. So you'd have 10 trillions, 100 trillions, so on and so forth. Now you can't possibly list everything, so at some point you just stop. Okay, so I've stopped here, but you can stop wherever you want. So now that we understand where these names are coming from and how this pattern works, let's think a little bit about this expanded notation that I showed you earlier. Essentially, we'll get to this in the next lesson in more detail, but for right now, just think about the digit multiplied by its corresponding place value. So you have a 1 in the thousands place. So basically that's 1 times 1,000 or just 1,000. So I'm just going to write that. Then I'm going to put plus. You have a 0 in the hundreds place. Now the 0 there is really a placeholder. It's telling me I don't have any hundreds in this particular number, but I need that 0 there to keep these other numbers in their correct positions. Otherwise, the number would collapse down and you'd have 152. Well, I don't have 152. I have 1,052. So I need that 0 there as a placeholder. With expanded notation, if you have a 0 somewhere, you could just skip it over. Then I have 5 tens. So that's 5 times 10, which is 50. And then plus I have 2 ones, so that's 2 times 1, which is 2. So this is the basic idea behind expanded notation that we saw in the last part of the lesson. All right, so let's just get a little practice writing a number inside of a place value chart. It's a very easy exercise. So 673,452. Let me grab this, come down here and paste this in. I would advise you to get a piece of paper and a pencil and try this on your own. Just make a place value chart. You don't have to go out to the trillions. This number is only going to go to the 100,000s, so you could just cut your paper off there. So I'm just going to take the rightmost digit of this whole number here, this 2, put that in the ones place. That's the rightmost position in this place value chart. So I'd put a 2 here. Again, as I work my way to the left in the number, I'm working my way to the left on the place value chart. So I'm just matching my movement. So this 5 would go into the tens, this 4 would go into the hundreds, this 3 would go into the thousands, this 7 would go into the 10,000s, and this 6 would go into the 100,000s. Okay, let's look at a bigger one. So now we have 7,853,922,673. So 7,853,922,673. You can grab this real quick. come down here and paste this in. All right, so I'm going to take my 3, which is the rightmost position of this whole number, and I'm going to put it in the rightmost position on this place value chart. So again, that's going into the ones place. So I'm going to put a 3 there, and I'm going to work my way to the left in the number, and I'm going to match that movement on my place value chart. So I'm going to the left and getting that 7. That's going to be in the tens place. Go to the left, I have a 6 that's in the hundreds place. Go to the left, I have this 2 here, which would be in the thousands place. And then go to the left, I have this 2, which is going to be in the 10,000s place. And then go to the left, I have a 9 that's in the 100,000s place. Now, as I go to the left, I have a 3 that's in the millions place. Go to the left, I have a 5 in the 10 millions place. Go to the left, I have an 8 in the 100 millions place. And then lastly, I go to the left and have a 7 in the billions place. All right, let's look at some standard questions now. So a typical place value test consists of questions that ask for the place value of a specified digit. So we're going to try a few examples. We want to find the place value for each underlined digit. So I went ahead and underlined them, and also I wrote them in a different color, and I'm going to come down here and paste this in. We'll do some with the place value chart, and then we'll do some without it. It's a really easy thing. Once you do a few examples, you sort of start to memorize the pattern, and then it's really, really easy to figure this out. So once again, I'm going to start with the rightmost digit of this whole number. I'm going to put it in the rightmost position in this place value chart. So the 1 would go here in the ones place. The 8 here, I'm going to the left, so I'm mashing that movement on my place value chart. The 8 here would go in the tens place. The 5 here would go in the hundreds place. The 3 here would go in the thousands place. The 7 would go in the 10,000s place. And then lastly, the 6 would go in the 100,000s place. So to answer our question, let me put a little border here. We would say for the 3, that's going to be where? That's going to be in the thousands place. So this is in the thousands. And you could put place if you want. I'm just going to put thousands. And then the 8 here, well, that's going to be in the tens place. So let's put the 8 is going to be in the tens place. All right, let's take a look at another example. So here we have 6,358,791. So let me just paste this in here. I'm going to start with the rightmost digit of the number. I'm going to put that into the rightmost position in our place value chart. So this 1 would go in the ones place, and then I'm going to work my way to the left in the number and then match that in my place value chart. So I'm going to have a 9 that's going to be in the tens place, a 7 in the hundreds place, an 8 in the thousands place, a 5 in the 10,000s place, a 3 in the 100,000s place, and then lastly a 6 in the millions place. Now we want to find the place value for the underlined digits. Let me put a little border here. So we have this 3, and that's going to be in the 100,000s place. So let's just write 100,000s here. And again, you can put place if you want. That's up to you. And then for the other one, it's going to be the 7, which is going to be right here. So that's going to be in the hundreds place. So let's put that the 7 is in the hundreds place. All right, let's look at one that's really big. So we have 9,551,072,636,010. So let me paste that in, and we're going to be looking for the place value of this guy, this 9, this 7, and this 3. So again, I'm just going to feed this into the place value chart. So the 0, the rightmost digit of that number, it's going to go into the rightmost position of the place value chart. So that 0 is in the ones place. Just going to work my way to the left here and match that in my place value chart. So I'd have a 1 in the tens place, a 0 in the hundreds place, a 6 in the thousands place, a 3 in the 10,000s place. Let me go ahead and highlight that since we have so much going on here. And then we're going to have a 6 in the 100,000s place, a 2 in the millions place, a 7 in the 10 millions place. So again, that's one of the ones that's underlined. So let me highlight that real quick. And then as we work our way to the left, we have a 0 in the 100 millions place, a 1 in the billions place, a 5 in the 10 billions place, and then also a 5 in the 100 billions place. And then lastly, we have a 9 in the trillions place. So let me highlight that and that, again, because it's underlined. Okay, so really not that bad. Let me put a little border here, and I'll slide down just a little bit. And let me put this around the number. Hopefully I can fit everything on the right of this border, but maybe I can't. We'll see. So for the 9, that is going to be in the trillions place. So I'm just going to write trillions. Again, if you want to write place, that is up to you. Then for the 7, that is going to be in the 10 millions place. So 10 millions. Again, you can put place there. And then for the 3, we are going to say that's in the 10,000s place. So let's put 10 thousands. And again, you could put place. All right, let's try a few without the place value chart. So I'm going to start with 7,036. So remember, the rightmost position of your whole number, that's in the ones place. You could just write ones like this. And if you're lost, again, as you move to the left, you're just multiplying by 10. So 1 times 10 is 10. So this next position to the left, that's in the tens place. And we can keep going even though we have our answer. Multiply 10 by 10, that's 100. So this position right here, this is in the hundreds place. And then I probably can't fit this here. Maybe I can just arrow down here like that. So going to the left one more time, 100 times 10 is 1,000. So this would be in the thousands place. So the answer we want is actually the tens place. Let me put the 3 over here. That's what's underlined. And we'll say this is in the tens place. All right, the next example, we have 64,114. I think we probably don't need to write things out at this point. So the rightmost digit of that whole number, again, that's in the ones place. As you move to the left, just multiply by 10. So you'd have the tens, the hundreds, the thousands. So that's what we're looking for. That digit 4 that's underlined here is going to be in the thousands. So the thousands place. Again, not this 4. This 4 right here would be in the ones place. We're talking about this 4 specifically that's underlined. That's going to be in the thousands place. All right, let's just look at one more. So a pretty big number. This is 1,998,004,557. So the guy that's underlined here is the 9. Now, one thing that you could do is by reading the number, you immediately say, okay, well, this is 1 billion. Well, what comes to the right of 1 billion? Again, you could just divide by 10. That's going to be 100 million. So immediately you know that 9 that's underlined is in the 100 millions place. But again, you could start here and say, okay, well, this is the ones. And every time I go to the left, that's going to be times 10. So tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, again, 100 millions. So however you figure that out, this digit here, this 9, is going to be in the 100. So the 100 millions place. And again, there's 2 9s here. So specifically, I'm talking about this one right here that's underlined. If you look at the one to the right of it, that would be in the 10 millions place, but we're not talking about that one because it's not underlined. So this one specifically, this 9, is in the 100 millions place. Hello and welcome to Pre-Algebra Lesson 2. And in this video, we're going to be learning about expanded notation. So our lesson objectives for today would be to learn how to write a number in expanded notation. And we also want to learn the difference between standard and expanded notation. So in our first lesson, we learned all about place value. I taught you how to use this place value chart to find the place value for all the digits in a given number. Now, when we think about expanded notation, all we're simply doing is we're writing a number in a way that it emphasizes the place value for each digit in that number. So this is kind of just a continuation of the last lesson. And in fact, in the first lesson, I gave you a couple of examples where we wrote a number in expanded notation. Now, let's say I took a number like 1,035. And we want to write this in expanded notation. Well, the first thing is we need the place value for each digit in the number. So let's feed this into the place value chart. So we start with the rightmost digit, and we put it in the rightmost column of the place value chart. So the 5 goes into the ones place. And as we move left on the place value chart. So the 3 goes in the tens place, the 0 goes in the hundreds place, and the 1 goes in the thousands place. So now that we know the place value for each digit in the number, we can write the number in expanded notation. All we need to do is form the sum of each digit multiplied by its corresponding place value. So starting with this 1 on the left, it's in the thousands place. So each digit, that 1, multiplied by its corresponding place value. If it's in the thousands place, we multiply it by 1,000. Then plus. Next, we have a 0 in the hundreds place. Now that 0, as I've previously explained to you, is just a placeholder. But to illustrate expanded notation, I'm going to go ahead and include it for now, although you don't have to. So the 0 here is multiplied by 100. Then plus, we have a 3 in the tens place. So that digit 3 is multiplied by 10. And lastly, we have a 5 in the ones place. So we'll have plus 5, that's the digit, times 1, the place value. Okay, let's do a little multiplication now. So 1 times 1,000 is 1,000. Plus 0 times 100 is 0. Plus 3 times 10 is 30. and then plus 5 times 1, that's 5. So let's just write this as 1,000 plus 30 plus 5, right? We don't need to include that 0. So essentially, when we write a number in expanded notation, you can see that it's emphasizing the place value of each digit. This 1 has a value of 1,000. This 3 has a value of 30. This 5 is still a 5. The reason this is still a 5 is because it's in the ones place. 5 times 1 is just 5. The reason this is a 30 is because it's in the tens place. 3 times 10 is 30. And the reason this 1 is 1,000 is because it's in the thousands place. 1 times 1,000 is 1,000. So it's a pretty simple concept overall. And remember, when we talk about this 0 here, it's a placeholder, right? It's a placeholder. We don't have any hundreds in this case, right? We don't have any hundreds in this case. But our number system will allow us to write 1,035 with this 0 saying, hey, I don't have anything there, but hold that space. Otherwise, what would you have? This 1 would collapse down and you wouldn't be able to tell the difference between 135 and 1,035. So you get all kinds of problems. So let's take a look at another one. Let's say we want to write the number 22,359 in expanded notation. Well, let's get the place value first. So I'm just going to feed this into the place value chart. The 9 goes in the ones place. The 5 goes in the tens place. The 3 goes in the hundreds place. The 2 goes in the thousands place. And then this 2 here is going to go in the 10,000s place. So to write the number in expanded notation, again, we form the sum of each digit multiplied by its corresponding place value. So there's a 2 for the digit times its corresponding place value. It's in the 10,000s place. So just 2 times 10,000. Plus, now we have a 2 in the thousands place, so 2 times 1,000. Plus, now we have a 3 in the hundreds place, so 3 times 100. Plus, we have a 5 in the tens place, so 5 times 10. And then lastly, plus, we have a 9 in the ones place, so 9 times 1. Let's do some multiplication. 2 times 10,000 is 20,000. Plus 2 times 1,000 is 2,000. Plus 3 times 100 is 300. Plus 5 times 10 is 50. And then plus 9 times 1, that's 9. So again, by writing this number in expanded notation, we can see the true value of each digit in the number. This 2 has a value of 20,000. This 2, let me do it in a different color because they're both 2's and are side by side. This 2 has a value of 2,000, right? It's in the thousands place. This 3 has a value of 300. This 5 has a value of 50. And then this 9 has a value of just 9. So each digit gets its value, again, based on where it is in the number, and that's why we call it a place value system. Let's look at another one. Okay, let's say we had 759,275. So let's feed this into the place value chart. So the 5 goes in the ones place, the 7 goes in the tens place, the 2 goes in the hundreds place, the 9 goes in the thousands place, the 5 goes in the 10,000s place, and the 7 goes in the 100,000s place. So to write this in expanded notation, again, we form the sum of each digit multiplied by its corresponding place value. So this digit is a 7. Its place value is the 100,000s place, so 7 times 100,000. 7 times 100,000. Then plus. Next we have a 5 in the 10,000s place. So 5 times 10,000. Then plus, we have a 9 in the thousands place. So 9 times 1,000. And plus, we have a 2 in the hundreds place. So 2 times 100. And plus, we have a 7 in the tens place. So 7 times 10. Then lastly, we have plus 5 times 1. Right? We have a 5 in the ones place. 5 times 1. So we do a little multiplication. 7 times 100,000 is 700,000. Plus 5 times 10,000, that's 50,000. Plus 9 times 1,000, that's 9,000. Plus 2 times 100, that's 200. Plus 7 times 10, that's 70. And then lastly, plus 5 times 1, that's 5. So by taking this number from standard notation and putting it in expanded notation, we can see the true value of each digit in the number. The 7 is 700,000, right, because it's in the hundred thousands place. The 5 is 50,000 because it's in the 10,000s place. 5 groups of 10,000, 50,000. The 9 is 9,000, right? It's in the thousands place. The 2 is 200, it's in the hundreds place. The 7 is 70, it's in the tens place. And lastly, the 5 is still a 5 because it's in the ones place. Let's look at another one. All right, for the next one, let's write 36,255,927 in expanded notation. Now, some of you might be going, well, where's the place value chart? At some point, you have to be able to do this without a place value chart. You have to simply memorize the place values. So if that's something you can't do yet, pull out a place value chart, write this number into the place value chart so that you can get the place value for each digit in the number, and then continue with me. But otherwise, remember that there's a trick you can use. And in case you didn't watch the first video where we talked about place value, I'll explain it for you. So the rightmost place you should be able to remember is the ones place. As you move to the left, you're just multiplying by 10. So in other words, if you think about this as just 1. As I move left, I multiply by 10. This would be 10, right? It's the tens place. It's the tens place. Then as I move left, again, I multiply by 10. This just keeps going forever and ever and ever. You just keep multiplying by 10. So 10 times 10 is 100. So this is the hundreds place. Okay, then this would be the thousands. And let me make that apostrophe a little better. And then this would be the 10,000s. And this would be the 100,000s. This would be the millions. And this would be the 10 millions. And again, the way you figure this out is the rightmost column is always the ones place. So you just think about it as just a 1. As you move to the left, you multiply by 10. So 1 times 10 is 10. So this is the tens place. Now I have a 10. Multiply by 10 again, you get to 100. So now this is the hundreds place. Multiply by 10 again, you get to 1,000. That's the thousands. Then 10,000, then 100,000, then a million, then 10 million, so on and so forth. That continues forever and ever and ever. So you could have a number as large as you want, and provided you had enough time, you could sit there and write out the place values for each digit in that number. Now, let's take this number and write it in expanded notation. So it's kind of a big number, so it's going to take a little time. We have a 3 that's in the 10 millions place, so we would have 3 times 10 million. Then plus, we have a 6 in the millions place, so 6 times 1 million. And plus, we have a 2 in the 100,000s place, so 2 times 100,000. And plus, we have a 5 in the 10,000s place, so 5 times 10,000. And plus, we have another 5, and that's in the thousands place, so 5 times 1,000. And plus, we have a 9 in the hundreds place, so 9 times 100. And plus, we have a 2 in the tens place, so 2 times 10. And lastly, we have plus 7 times 1, right? We have a 7 in the ones place. So we do a little multiplication. 3 times 10 million is 30 million. 30 million. And again, that's telling me that the value of this 3 here is 30 million. Then plus, we have 6 times 1 million, which is 6 million. 6 million. So the value for this 6 is 6 million. Then plus, we have 2 times 100,000, or 200,000. The 2 is worth what? 200,000. Then next we have 5 times 10,000, so plus 50,000. 50,000. So this 5 is 50,000. Then plus, we have 5 times 1,000, which is 5,000. So 5,000. So this 5 is a 5,000. And then we have plus 9 times 100 or 900. So this 9 is worth 900. And then plus, we have a 2 in the tens place, so 2 times 10 or 20. So this 2 is a 20. And then lastly, we just have plus 7, right? 7 times 1 is 7. This is just a 7. So your number, 36,255,927, written in expanded notation, looks like this. 30 million plus 6 million plus 200,000 plus 50,000 plus 5,000 plus 900 plus 20 plus 7. So again, just breaking it down and showing you the true value of each digit in that number. Okay, for the last example, let's look at one that's really big. So we have 10 billion, 5,327,005. Now the good thing about this number is I included a lot of zeros. And when you have zeros and you write a number in expanded notation, you can skip them. So in other words, I'll have this 1 here. This is in the 10 billions place. Because essentially this is the ones, the tens, the hundreds. This is the thousands, the 10,000s, the 100,000s. This is the millions, the 10 millions, the 100 millions. Then this is the billions and the 10 billions. Okay? So this 1 is in the 10 billions place. So I'd have 1 times 10 billion. Then plus. Now all these zeros are basically just placeholders. So when we write the number in expanded notation, we don't have to put them. So I can kind of just skip down to the next non-zero number. So that's a 5, and that's going to be in the millions place. So 5 times 1 million. Then plus. Next I have a 3 in the 100,000s place. So 3 times 100,000. And plus, I have a 2 in the 10,000s place, so 2 times 10,000. Then plus, I have a 7 in the thousands place, so 7 times 1,000. Then plus, I have a 5 in the ones place, so 5 times 1. Let's do a little bit of multiplication here. 1 times 10 billion is just 10 billion. Okay, then we have plus 5 times 1 million is 5 million. Then plus 3 times 100,000 is 300,000. And plus 2 times 10,000, that's 20,000. And plus 7 times 1,000 is 7,000. And plus 5 times 1, which is 5. So again, all we're doing is we're breaking the number down to see the value for each digit in this number. So this 1 is a 10 billion. This 5 is a 5 million. This 3 is a 300,000. This 2 is a 20,000. This 7 is a 7,000. And then lastly, the 5 is just a 5 because, again, it's in the ones place. 5 times 1 is just 5. Hello and welcome to Pre-Algebra Lesson 3. In this video, we're going to learn about inequalities and the number line. All right, so the lesson objectives for today, we want to learn how to create and work with a number line for the whole numbers. And then also we want to learn about inequalities and a few symbols we're going to work with. So previously in our course, during the lesson on place value, we introduced the whole numbers. So the whole numbers start with 0. So that is the smallest whole number. And then they increase in increments of 1 out indefinitely. So after 0 comes 1, then 2, then 3, then 4, then 5. You just pick a spot because you can't list all of them. And you're going to stop. And you can put the 3 dots there just to show that the pattern continues forever. So after 5 comes 6, then 7, then 8, so on and so forth. Now we can visually represent our whole numbers using a horizontal number line. And so the leftmost notch here is going to correspond to the smallest whole number, which is 0. So see, this guy would correspond to this guy here. And then as we move to the right on the number line, each additional notch is corresponding to the next largest whole number. So this, going to the right by 1 unit, this would be 1. The next largest whole number is 1. Then this notch going to the right would be 2. The next largest whole number is 2, so on and so forth. You're just increasing by 1 each time. So you go to 3, then 4, then 5, then 6, so on and so forth. Now, in a similar way, to this guy right here where we put the 3 dots, we need to show that the whole numbers continue going out to infinity. So basically they continue forever. So what we're going to do here is draw this little arrow and say that, hey, after 10 comes 11, then 12, then 13, so on and so forth. Now there's a few things we want to think about when we look at the number line. First off, numbers increase from left to right. So you can pick any 2 numbers you want and just think about them for a moment. Let's say I start with something easy like 1 and 2. Well, I know that 2 is a larger number than 1, and notice how 2 is to the right of 1 on the number line. Let's just pick 2 other ones. So let's say we look at 6 and 7. Well, 7 is a larger number than 6, and notice that 7 is to the right of 6 on the number line. So as we move to the right, numbers are increasing in value. So what you can say is that if a number is to the right of another number on the number line, it is a larger number. Then additionally, we can say that numbers decrease from right to left. So if I'm going this way, numbers are decreasing in value. Let's take 4 and 5. Well, 4 is to the left of 5 on the number line, and 4 is a smaller number. So what you can say here is that if a number is to the left of another number on the number line, it is a smaller number. All right, before we move on with the lesson, we need to introduce a few new symbols. So the first symbol I'm going to talk about is the equality symbol. A lot of people just call this the equal sign or equals. So let me put that up there. I'm sure you've seen that before. So this means is equal to. So whatever's on the left is equal to whatever's on the right. You could also think about this as saying whatever's on the left is the same as whatever's on the right. Now, it's not always going to be very straightforward. So let's say I start with something very easy to identify as being equal or the same. So I'm going to put a 5 here and a 5 here. So obviously 5 is equal to 5, or 5 is the same as 5. If I have $5 in my wallet and my friend has $5 in his wallet, well, we have an equal amount of money or the same amount of money. We can each go to the store and buy $5 worth of stuff. Now, let's say we change up the way this looks a little bit. And to give you an example, let's say I keep my $5 bill in my pocket, but my friend goes to a bill changer and he exchanges his $5 bill for 5 singles, or you could say 5 $1 bills. One way you could write this is by showing this as 1 plus 1 plus 1 plus 1 plus 1. So now it doesn't look as straightforward as this, but these two sides represent the same value in the end. If he goes through and adds up his singles, he still has $5, right? This is 1 plus 1, which is 2, plus 1, which is 3, plus 1, which is 4, plus 1, which is 5. So each of us can go to the store and spend $5 on stuff. We have the same amount of money or an equal amount of money. So 5 is equal to or the same as 1 plus 1 plus 1 plus 1 plus 1. At the end of the day, the value on each side is 5. So another symbol we're going to use is the not equal to symbol. So here we're going to draw the equal symbol and we're going to put a little slash through it. So this means is not equal to. So whatever's on the left is not equal to whatever's on the right. Now it doesn't matter what's on the left and what's on the right as long as they're not equal. So you could have a smaller number on the left and the larger number on the right, or you could put the larger number on the left and the smaller number on the right. It does not matter. So what I'm going to do is say something like, let's say 5 is not equal to 7. So let's say my friend got $2 additional, and so now he has $2 more than me to spend. He can spend $7, but I can only spend $5. So the amount of money we have is not the same. It's not equal. Again, this can also be more complicated. So let's say that I have a 5 here, and let's say over here, keeping with what we did a moment ago, let's say we have 1 plus 1 plus 1 plus 1 plus 1. So that's my 5 ones. And let's add an additional 2 here. So here we have 1 plus 1, which is 2, plus 1, which is 3, plus 1, which is 4, plus 1, which is 5, plus 1, which is 6, plus 1, which is 7. So 5 is not equal to, at the end of the day, 7. So it doesn't matter if it's straightforward like this. You're going to see a lot of stuff that's not straightforward, and you need to go through and think about, well, what is the value of this once I perform this operation? Well, this would be 7, and this is 5, and 5 is not the same as 7. So here we can show that with the not equal to symbol. All right, now the next two symbols we'll use for the rest of this lesson. These are called the strict inequalities. We'll talk about non-strict inequalities later on, but for right now, when you talk about a strict inequality, you're talking about a less than symbol or a greater than symbol. So let's start with a less than symbol. So this right here means is less than. So whatever's on the left is less than whatever's on the right. So the way you remember this, when you're looking at these symbols, this guy right here is always pointing to the smaller number. So if I grab two numbers from the number line, let's say 2 and 3, again, 2 is smaller than 3 because 2 is to the left of 3 on the number line. In order to make this a true statement, I need to put that smaller number on the left and the larger number on the right. So it's very important that you do it this way. If you put here that 3 is less than 2, that's a false statement, okay? So with this one, you want to make sure that the smaller number is on the left and the larger number is on the right. So you can say that, in this case, 2, or whatever that smaller number is less than the 3, or whatever that larger number is. Then the other guy is going to be the greater than symbol. So this means is greater than. So now the number on the left is larger than the number on the right. So here the number on the right needs to be smaller. The symbol always points to the smaller number. Here it points to 2 because 2 is smaller than 3. Here it's going to point to, let's just pick two numbers. Let's say we go with 8 and 9. So here it would point to 8 because 8's a smaller number. It's to the left of 9 on the number line. 9 needs to go over here because it's the larger number. So we would say 9 is greater than 8. So whatever the bigger number is goes on the left, and that's greater than whatever the smaller number is, that's going to go on the right. All right, let's go through some examples. I think you're going to find this very, very easy, but something you'll definitely see in your textbook. So we want to replace each question mark with the inequality symbol less than or greater than. All right, for the first example, we have 5 question mark 2. So let me write this over here. 5, and then we have a question mark, and then a 2. So first, let's circle 5, and then let's circle 2. So 5 is to the right of 2 on the number line, so 5 is a larger number than 2. So here I would want to use a greater than symbol. Again, if you can't remember, the symbol always points to the smaller number. 2 is a smaller number than 5, so just point the symbol to the smaller number. So here you would say 5 is greater than 2. Now, if we flip this around, and let's say the problem was 2, question mark 5, then now we want to use a less than symbol. Always point the symbol to the smaller number. So this guy right here would point towards 2. 2 is less than 5. Here, 5 is greater than 2. With a greater than, the larger numbers on the left. With a less than, the smaller numbers on the left. All right, for the next problem, we'll look at 3 question mark 0. Here's 3. Here's 0. So 3 is to the right of 0 on the number line, so 3 is going to be a larger number. So we would say that 3 is greater than 0. Again, that symbol is going to point, let me use a different color here, is going to point to that smaller number. 0 is the smaller number. If you flip this around, and let's say you got 0 and then question mark 3, well now I want to use a less than. 0, which is the smaller number, is less than 3. The symbol always points to the smaller number. What about the next one? We have 4 question mark 8. So 4 question mark 8. Here's 4, here's 8. So 4 lies to the left of 8 on the number line, so it's a smaller number. So here we would want to use the less than symbol. Again, the symbol is going to point to the smaller number. If we had gotten 8 question mark 4, well now we want to use the greater than symbol. 8's a bigger number. It lies to the right of 4 on the number line, so we would want to say 8 is greater than 4. What about 7 question mark 3? So 7 question mark 3. Here's 7, here's 3. 7 lies to the right of 3 on the number line, so it's a bigger number, so you want to use a greater than there. Again, the symbol always points to the smaller number, so the symbol would point to 3. If you had gotten 3 question mark 7, well now you want to use your less than symbol to say 3 is less than 7. Symbol always points to the smaller number. What about 1 question mark 2? Here's 1, here's 2. So 1 is to the left of 2 on the number line, so you would say 1 is less than 2. Symbol always points to the smaller number. If you got 2 question mark 1, well then you want to use the greater than symbol. 2 is a larger number than 1. The symbol always points to the smaller number. The smaller number here is 1. Hello, and welcome to Pre-Algebra Lesson 4. And in this video, we're going to learn about rounding whole numbers. So our lesson objective for today is simply to learn how to round whole numbers. So before we get into the procedure that we use to round a whole number, let's talk a little bit about why we would round whole numbers. So in many situations, an exact value is not needed. In these cases, an approximation is easier to use and remember. And when we talk about approximations, we're talking about a value that is close to the original value, but not exactly there. All right, so rounding a whole number. The first thing you want to do is locate the digit in the round off place. So for example, if we are rounding to the nearest 10, you would start by locating the digit in the tens place. When you first start out, I would circle that digit or highlight it or do something to say, hey, this is my round off place. So kind of step 2 is to look at the digit to the right of the round off place. So if the digit to the right of the round off place is, and you have two different scenarios. The first one is 4 or less. You want to leave the digit in the round off place unchanged. Then the second scenario that could occur is that it's 5 or larger. In this case, we increase the digit in the round off place by 1. Okay, increase the digit in the round off place by 1. And then your third and final step is pretty easy. You just replace each digit to the right of the round off place with a 0. Okay, here we want to round 631 to the nearest 10. So again, I'm looking for the tens place, and that's going to be this 3 here. And then in step 2, what I want to do is I want to look at the digit to the right, and that's going to be this 1. Now, does this 1 fall in the category of 4 or less, or does it fall in the category of 5 or larger? Well, it's clearly in the category of 4 or less. So when that happens, I want to leave the digit in the round off place, which is the 3, right? It's in the tens place, unchanged. So I would have 6, and then the 3 is going to be unchanged. And then in step 3, I'm going to replace each digit to the right of the round off place with a 0. So the 1 is to the right of the round off place. I'm going to replace that with a 0. And so 631 rounded to the nearest 10 is 630. Okay, next we want to round 7,952 to the nearest 1,000. So 7,952. And we're looking for the digit in the thousands place. So that's going to be this 7 here. And then we look for the digit immediately to the right of that. So that's this 9. And obviously the 9 falls in the category of 5 or larger. So when this occurs, we increase the digit in the round off place by 1. So I'm going to increase that 7 by 1. 7 plus 1 is 8. And then I replace each digit to the right of the round off place with a 0. So I'm going to replace the 9 with a 0, the 5 with a 0, and the 2 with a 0. And so 7,952 rounded to the nearest 1,000 is 8,000. Okay, next we want to round 813,275 to the nearest 10,000. All right, so we have 813,275, and the 10,000s place is right here. So I'm looking at the digit that follows that, and that's this 3 here. 3 falls in the category of 4 or less. So when this occurs, we're going to leave this digit in the round off place unchanged. Unchanged. So the 8 and the 1 are going to stay unchanged. I don't need to do anything to those. But I'm going to replace each digit to the right of the round off place with a 0. So the 3 is to the right of the 1, so I'm going to replace that with a 0. And then I'm going to replace the 2, the 7, and the 5. And so 813,275 rounded to the nearest 10,000 is 810,000. Okay, for the last problem, we want to round 61,005,387 to the nearest million. So 61,005,387 to the nearest million. So the millions place is right here. That's the 1. And we want to look at the digit to the right of the 1. So I'm looking at this digit here, which is a 0. 0 is obviously in the category of 4 or less. So we're going to leave the digit in the round off place unchanged. Unchanged. So basically the 6 and the 1 will be unchanged. And then everything that follows the 1, which is the digit in the round off place, will just be a 0. So I'll have 0, 0, 0, comma 0, 0, 0. So 61,005,387 rounded to the nearest million is 61 million. Hello and welcome to Pre-Algebra Lesson 5. And in this video, we're going to learn about the properties of addition. Okay, so for the lesson objectives, we want to learn about the identity property of 0. We want to learn about the commutative property of addition. We want to learn about the associative property of addition. And then also we want to learn to identify the parts of an addition problem. Okay, so let's begin the lesson by thinking about what addition actually is. So addition is the operation that allows us to group items together. So if we think about this in a very simple way, kind of the way that you would think about it if you're in grammar school, we have this picture here, and we have 3 boxes, and we're adding to that 2 more boxes. So we can just go through and count how many boxes we have. We can just say, okay, I have 1, 2, 3 boxes, right, from up here. And then I added to that 2 more. So then 4 and then 5. And at this point, we all know that 3 plus 2 is 5, but this just visually represents what's going on when we add. We're trying to get a total for all the amounts that we've combined together, right? I've combined this group of 3 boxes with this group of 2 boxes, and it gave me a total of 5 boxes. Okay, so let's talk about a little bit of vocabulary. So in an addition problem, the numbers being added together are called addends. Okay, addends. And then the result of an addition operation is known as the sum. Okay, the sum. So let's look at a quick problem. We want to identify each part of the addition problems below. Okay, so we're going to start with 5 plus 6 equals 11. And all we're going to do is just label. So we know that the numbers being combined together or added together are called addends. So 5 and 6 would be addends. And then 11, which is the result of the addition, would be called the sum. Okay, let's look at the next one. We have 12 plus 8 equals 20. So 12 and 8 are the numbers being added together. Those are called addends. So these are the addends. And again, the result of the addition is called the sum. So 20 is the result of 12 plus 8. So this is the sum. Okay, so the first property we're going to learn about today is called the identity property of 0. And it's really pretty simple. It just tells us that adding 0 to any number leaves the number unchanged. Okay, so I can add 0 to any number and it will remain unchanged. So let's take a look at some examples here. So 5 plus 0 equals what? Well, adding 0 to 5 leaves 5 unchanged, so 5 plus 0 equals 5. 7 plus 0 equals what? Adding 0 to 7 leaves 7 unchanged, so 7 plus 0 equals 7. And then 1,365,371 plus 0. Again, adding 0 to anything leaves it unchanged, so it would just be 1,365,371 as the answer. Okay, the next property is also very simple. It's called the commutative property of addition. And the commutative property of addition tells us we can add numbers in any order without changing the sum. So the order that you add does not matter whatsoever. And kind of to prove this, I have some examples. So we have 6 plus 3 equals 3 plus 6. Basically, the order is changed. So 6 is on the left here. 6 is on the right over here. It doesn't matter. You're going to get 9 either way, right? If I say 6 plus 3, what does that equal? It equals 9. If I say 3 plus 6, what does that equal? It equals 9. So changing the order of the addends does not change the sum. Again, as another example, 7 plus 9 equals 9 plus 7. So changing the order here of the addends does not change the sum. 7 plus 9 is 16, and 9 plus 7 is 16 as well. And as a final example, we have 12 plus 5 equals 5 plus 12. Again, switching the order or changing the order of the addends does not affect the sum. 12 plus 5 is equal to 17. 5 plus 12 is also equal to 17. Okay, so the last property we're going to talk about today is another easy one. It's known as the associative property of addition. And the associative property of addition tells us that the addition of 3 or more numbers can be grouped in any order without changing the sum. So the way that we group numbers when we're adding does not change the sum. So let's look at some examples of this. We have 3 plus 6 here on the left, and that's inside of parentheses. And then we're adding to that 2, and we're saying that's equal to 3 plus, and here we have 6 plus 2 inside of parentheses on the right. Now the associative property is telling us that since we're adding the same 3 numbers, 3 plus 6 plus 2, it doesn't matter what we put parentheses around. We're going to get the same result. We haven't done a lesson on the order of operations yet, but the order of operations tells us that if you have operations inside of parentheses, you have to do them first. So if we were to follow that rule, we would say 3 plus 6 is 9. We would do that operation first, and then we would add 2 to that. So 9 plus 2 gives me 11. So kind of the left side here gives me a result of 11. On the right, I would do 6 plus 2 first because that's inside of parentheses. 6 plus 2 is 8, so we would have 3 plus 8, and that equals 11 as well. So it didn't matter that we had parentheses here on the left around 3 plus 6 and parentheses on the right around 6 plus 2. We got the same result either way. And that's exactly what the associative property of addition is telling us. Okay, for another example, we have 7 plus 5 plus 2, and 5 plus 2 is inside of parentheses. And this is equal to 7 plus 5. Now 7 plus 5 is inside of parentheses plus 2. So 7 plus, and a lot of times you'll hear that people say the quantity when something's inside of parentheses. So 7 plus the quantity 5 plus 2. 5 plus 2 is done first. 5 plus 2 is 7. So we get 7 plus 7, and that gives us 14. So the left side here is 14. What's the right side going to be? It's going to be 14 as well. The quantity 7 plus 5 is 12. Again, we're doing that first because it's inside of parentheses, and then plus 2 gives us 14. So again, we group this different in each case. We have 5 plus 2 inside of parentheses on the left. We have 7 plus 5 inside of parentheses on the right, but it didn't matter, right? Because we got 14 either way. Okay, as our last example, we have 15 plus 9 inside of parentheses. So the quantity 15 plus 9 plus 2, and this is equal to 15 plus, now we have parentheses around 9 plus 2, so 15 plus the quantity 9 plus 2. So on the left here, we start with 15 plus 9 because that's in parentheses. So the quantity 15 plus 9 is 24. 24. Then plus 2 would give me 26. On the right, I'm going to do 9 plus 2 first. So the quantity 9 plus 2 is 11. So we'd have 15 plus 11. And of course, that gives us 26 as well. So again, that's what the associative property of addition is telling us. We have the same 3 numbers being added, 15, 9, and 2. We're going to get 26 no matter how we group the addition. We can put parentheses around 15 plus 9. We can put parentheses around 9 plus 2. It doesn't matter. We get 26 as a result either way. Hello and welcome to Pre-Algebra Lesson 6. And in this video, we're going to be learning about adding whole numbers using a number line. So the lesson objective for today will be to just learn how to add whole numbers, again, using a number line. So during a previous lesson, we talked about using a number line to visually represent a group of numbers. So let's look at a number line that shows the whole numbers. And again, I've talked about the whole numbers in previous lessons. The whole numbers are a group of numbers that start with 0. So 0 is your smallest whole number. And then they increase in increments of 1. So after 0, you get 1, then 2, then 3, then 4. Again, just increasing in increments of 1. And this continues forever. And that's why we have the 3 dots here. When you see the 3 dots in this case, it means that the pattern, which we're increasing in increments of 1, is going to continue forever. So after 4 comes 5, then 6, then 7, so on and so forth. So if we look at the whole numbers using a number line, again, this is a number line. This is a visual representation of the whole numbers. So you'll see the leftmost whole number is 0. That's your smallest whole number. And you see you have a little notch here. Now, every time you have another notch as you move to the right, you're going to the next largest whole number. So you go to 1, then you're going to 2, then you're going to 3, then you're going to 4, so on and so forth. So it's impossible to list all the whole numbers. So basically what we do is at some point we just stop and it can be basically anywhere. I could have stopped this at 5. You just draw an arrow to say, hey, this is going to continue forever. Okay, so we can use the number line to visually show the addition of whole numbers. So this may seem like a trivial exercise, but it will help us a lot when we start working with integers. So this is going to seem kind of like it's a waste of time to you at first, but when you start working with integers, especially for the first few times that you work with integers, with addition and subtraction, it's a lot easier to start out doing it on a number line. And if you already had that experience doing it with whole numbers, it'll make it a little bit easier for you when you do it with integers. So how do we add whole numbers on a number line? Well, we start at the leftmost number. So for example, if you had 3 plus 7, you would start out at 3 on the number line, and then you move to the right by the number of units being added. So we're adding 7 to 3, so we would just move to the right by 7 units. It's actually very, very, very simple. So let's take a look at some examples now. We want to add 2 plus 6 using the number line. So the leftmost number, the 2, is where we're going to start on the number line. So we're just going to start right here. And then we're adding 6. Okay, we're adding 6. So I'm just going to go 6 units to the right, and I'll be at my answer. So I'm going to go 1, 2, 3, 4, 5, 6 units to the right. I'm at 8. So that is my answer. And all of us know at this point that 2 plus 6 is 8. So 2 plus 6 equals 8. It's just to get the practice of doing it on the number line. Okay, now we want to add 4 plus 7 using a number line. And so I have a number line that's a little bit larger. It's a little bit more crowded. But we can still find everything. We're adding 4 plus 7. So we're going to start at the leftmost number, or the 4. And that's going to be right here. This is your 4. And then you're adding 7. So we're just going to move 7 places to the right. So each notch is a place or increased by 1. So 1, 2, 3, 4, 5, 6, 7. So that's going to put us right here at 11. Okay, at 11. And again, we all know that 4 plus 7 is 11. Again, it's just to get the practice of doing it on the number line. So 4 plus 7 equals 11. Okay, now we want to add 6 plus 5 plus 1 using a number line. Although we're adding 3 numbers, the process is basically the same. We're starting at this leftmost number, so we're starting at 6. So that's going to be right here. And then we're going to go 5 places to the right because we're adding 5. So 1, 2, 3, 4, 5. So that puts us at 11. And we all know that 6 plus 5 is 11. Now we're adding 1 more, so we just go 1 more place to the right. So 1 more place to the right. That puts us at 12. And so our answer for 6 plus 5 plus 1 is, of course, equal to 12. Okay, now we want to add 3 plus 2 plus 1 plus 7, again, using a number line. So let's find 3. That's where we're going to start, the leftmost number. And that's right here. That's this guy. And we're going to move 2 places to the right because we're adding 2. So that's going to go 1, 2 places to the right. And now we're adding 1. So we're going to go 1 more place to the right. And then we're adding 7. So we're going to go 7 places to the right. 1, 2, 3, 4, 5, 6, 7. So we end up here at 13. So 3 plus 2 plus 1 plus 7 equals 13. And I kind of checked this since we can all do addition. 3 plus 2 is 5. 5 plus 1 is 6. 6 plus 7 is in fact 13. Essentially, you're just starting at the leftmost number of the addition problem. Every time you add something, you just move that number of places to the right on the number line. So we started at 3. We moved 2 places to the right to get to 5. Then we moved another place to the right to get to 6. And then we moved 7 places to the right to get to our final answer of 13. Okay, let's look at the final one. We want to add 2 plus 3 plus 5 plus 4 plus 7 plus 1 using a number line. So again, we're going to start at the leftmost number. So that's 2. So we'll start out here on the number line. And every time I add something, I just move that number of places to the right. So I'm adding 3, so I just want to go 3 places to the right. So 1, 2, 3 places to the right. So that put me at 5. Then I'm adding 5, so I'm going 5 places to the right. Let me just change colors. So 1, 2, 3, 4, 5 places to the right. So that would put me at 10. Then I'm adding 4. So now I'm going to go 4 places to the right. So 1, 2, 3, 4 places to the right. That's going to put me at 14. I'm adding 7 to that. So that's going to put me 7 places to the right. 1, 2, 3, 4, 5, 6, 7 places to the right. That's going to put me at 21. And then lastly, I'm going to add one more to that. So that is going to put me at 22. So that's my final answer here. It's 22. So we have 2 plus 3 plus 5 plus 4 plus 7 plus 1. And the answer is 22. And to check that, just go through and do your addition. 2 plus 3 is 5. 5 plus 5 is 10. 10 plus 4 is 14. 14 plus 7 is 21. 21 plus 1 is 22. So again, adding whole numbers on a number line seems pretty trivial. It's actually very, very easy, but it's going to help us when we get to adding integers. And again, what we do is we start at the leftmost number of the addition problem on the number line, and then every time we add a number, we move to the right on the number line by that number of units. Hello and welcome to Pre-Algebra Lesson 7, and in this video we're going to learn about vertical addition. So the lesson objectives for today would be to learn how to properly set up and perform vertical addition, and also to learn the process of carrying. Okay, so when are we going to use vertical addition? Well, vertical addition is a process we use when we're adding multi-digit numbers together. And a multi-digit number is any number that is larger than one digit. So to perform the vertical addition, the first step is to arrange the numbers to be added vertically, and by place value. So when I say vertically, I mean we're going to stack the numbers on top of each other. Let me just show you real quick with an example. Let's say we're adding 13 to 24. So 13 plus 24 is the problem. In this first step, we're just going to put the numbers on top of each other. Doesn't matter which number's on top or which number's on bottom. So 13 and 24, we're going to write like this. And there's more to it, but we'll get to those in the next steps. Now, notice how when I stack these numbers on top of each other, the digits in the ones place for each number line up, and the digits in the tens place for each number line up. This is your ones, and this is your tens. Let me just make this a little cleaner. This is the ones. Okay, so that is the first step. Stack the numbers on top of each other and by place value. So don't do something like this where you have 13 and 24 over there. That won't work. Again, vertically and then by place value. All right, so let's take a look at the second step. So let me just rewrite this. We have 13 and we have 24 written like this at this point. And for step 2, we want to draw a horizontal line underneath the bottom number. So let's do that. And place a plus symbol, okay, this is the plus symbol, to the left of the bottom number. So to the left of this bottom number, I'm just going to put a plus symbol. And now we have our addition problem set up. And in step 3, we're going to learn how to actually perform the addition. Okay, so for step 3, let me just rewrite this. We have 13 plus 24. We want to add the numbers in each column, starting with the ones column and moving left. So that means we're going to start in this column. You always work right to left when you're doing vertical addition. Now, we want to place the result directly below the horizontal line. So I'm going to start with the numbers in this column here. We're starting in the ones column. So what is 3 plus 4? 3 plus 4 is 7. So all I'm going to do is I'm going to put that directly below this horizontal line, and I got to stay in line. Basically, this 7 is going to be in the ones place for the answer. And then I just move left. So next I'm going to do the addition in the tens column. So I'm doing the addition here. So now I'm doing 1 plus 2, and that gives me 3. So when we add 13 and 24 together, we get 37. Okay, so let's take a look at some examples here. We're going to start with some very easy problems, and then we'll progress to some that are a little bit more challenging. So we have 27 plus 12. Again, we're going to begin by stacking the numbers on top of each other. So 27 can go on top, 12 can go on the bottom. And again, you can reverse that order. You could put 12 on the top and 27 on the bottom. It really doesn't matter. Now we're going to draw a horizontal line beneath the bottom number, and we're going to put a plus symbol off to the left of that bottom number. Now, we start by adding the numbers in the ones column. So we have 7 plus 2, and that gives us 9. Put your answer down in the ones column. Just keep following straight down. Then we move to the left. So now we're going to look at adding the numbers in the tens column. So 2 plus 1 is 3. So 27 plus 12 is 39. Let's kind of break this addition problem down a little bit further. If we think about 27 plus 12, again, we did it like this. 27 plus 12. We added in the ones column. 7 plus 2 is 9. We add in the tens column. 2 plus 1 is 3. We got an answer of 39. But if we think about 27, it's what? It's 2 tens, or 20, plus 7 ones, or 7. If we think about 12, it's 1 10, or just 10, plus 2 ones, or 2. So we think about adding these numbers together, just looking at them like this, it makes sense to have, okay, we want 7 ones plus 2 ones to know the amount of ones that we're going to have in our answer. So that's why those are lined up. So 7 plus 2 is 9. You get 9 ones. And it makes sense to think about the tens together as well. We have 2 tens plus 1 10, or we have basically 20 plus 10, or 30. So we have 3 tens. And when we think about this, this is basically 30 plus 9, or 39. So very important to translate this longer process into this shorter process here. This is just a shorthand for this over there. Now, what if you didn't stack the numbers up by place value? You'd run into a mess. You'd never get the right answer. If we think about 27 plus 12, let's say I did it like this. Let's say I put 27 here, and I don't know, let's say I put 12 over here. Would I get the right answer? Well, no, because now I think I only have 7 ones. So this would just come straight down. And now I think I have 2 tens plus another 2 tens, or 4 tens, or 40. And this would come down. So I get an answer of 147, which is completely incorrect, right? Completely incorrect. So that's why it's important to line up your numbers by place value. It's going to tell you how much of each you're going to have. How many ones, how many tens, how many hundreds that you're going to have in your answer. Okay, let's look at the next one. We have 405 plus 314. So again, we're going to line these up vertically and by place value. So everything is lined up. We got the ones, the tens, and now the hundreds. So we work right to left. So we're going to start by adding the numbers in the ones column. What is 5 plus 4? That is 9. So you're going to write your 9 in the ones column for the answer. 5 ones plus 4 ones going to give me 9 ones. Then we're just working our way to the left. So now we're going into the tens column. 0 plus 1 is going to give me 1. And we worked our way to the left again. Now we're in the hundreds column. 4 plus 3 is going to give me 7. And so my answer is 719. And again, just thinking about this, we had 5 ones plus 4 ones. That gave us 9 ones. We had 0 tens plus 1 10, which gave us 110. Then we had 4 hundreds plus 3 hundreds, which gave us 7 hundreds. So essentially we have 700 plus 10 plus 9, or the number 719 as our result. Okay, now we have 2,057 plus 14,112. So again, we're going to stack these numbers on top of each other and by place value. But one thing you're going to notice here is that one of the numbers has fewer digits than the other. Typically when this happens, you put the number with more digits on top. So typically you're going to see 14,112 on top and 2,057 on the bottom. But I'm going to do this addition problem twice and show you that it doesn't actually matter. This is just a little bit easier. So we're going to start in the ones column. 2 plus 7 is 9. Then we're going to the tens column. 1 plus 5 is 6. Then we're going to the hundreds column. 1 plus 0 is 1. And then I'm going to put a comma there. And now I'm going into the thousands column. So 4 plus 2 is 6. And then I'm going to the 10,000s column. And you'll notice how there's nothing here to add with 1. Typically, we'll teach this as, okay, just bring the number down. and you'll put a 1 there. So your answer is 16,169. Let's say I change what's on top. Let's put 2,057 on top, and let's put 14,112 on the bottom. Let's kind of move that over a little bit. And it's the same thing. We start in the ones column. 7 plus 2 is 9. Then we move to the left. 5 plus 1 is 6. 0 plus 1 is 1. 2 plus 4 is 6. And then bring down the 1. We get 16,169 either way. Just typically you're going to see this setup because the number with more digits is generally going to be on top. Okay, now we want to look at a problem that's going to involve something known as carrying. So I'm going to work through this problem and then I'm going to go back and explain how it works. So 27 plus 35 is what we're going to work on. So 27 plus 35. So what happens is when we try to add the numbers in the ones column, 7 plus 5, you get 12. I can't fit a 12 in this space right here. I can only fit numbers 0 through 9. I can only fit a digit in this space. So 12 is too big. So what I'm going to do, I'm going to break 12 apart. I'm going to think about the left number and I'm going to think about the right number. So the right number is going to stay. It's going to stay right here in the answer column, just like you normally would do. And then the left number is going to get carried into the next column. Okay, so we're going to carry the 1 into the next column. And now I'm just going to include it with the addition of that column. So 1 plus 2 plus 3. 1 plus 2 is 3. 3 plus 3 is 6. So we end up with 62. But let's think about what we actually did here. Let me just erase this real quick and think about what we actually did. When we look at 27 and we break it down, we have 2 10s plus 7 1s. Okay, so this is 20 plus 7. And when we think about 35, we have what? We have 3 10s, or we have 30, plus we have 5 1s, or just 5. So when we add the numbers in the ones column, we have 7 ones and we have 5 ones. 7 plus 5 is 12, so we would have 12 ones. Basically all we're doing is rewriting 12 ones as 1 10 plus 2 ones. Okay? 1 10 plus 2 ones. So when we think about the result here, if I give you a $10 bill and 2 ones, that's the same as if I handed you 12 ones. It's the same. So all I'm doing here is I'm just going to scratch this out, and instead of putting 12 ones, I'm going to put 2 ones, and then I'm going to go into the next column, into the tens column, and say, hey, I have another 10. I have another 10. So now the result of the addition, we have 10, 20, and 30 that we're adding. 10 plus 20 is 30. 30 plus 30 is 60. So we end up with 6 10s, or 60, plus 2 ones, which is 62. That's what we got. So this is essentially what we're doing when we're using the carrying process. It's just a shorthand way to kind of go through and do all this and evaluate place values. Let's take a look at another one. Okay, next we have 242 plus 977. So 242 plus 977. So again, we're going to start by adding the digits in the ones column. So 2 plus 7 is 9. And then we work our way to the left. So next we're looking at the tens column. So we have 4 plus 7, but that's 11. And I cannot fit an 11 right there. You cannot fit anything larger than a 9 in this space. So what we need to do is evaluate the place values and figure out what we need to do. So we use carrying to do that. So if I have 11, I take the rightmost digit of 11, and that's a 1, and I put that in the answer column. So that goes there. Then I carry the leftmost digit, which is also a 1, into the next column. So that's going to go right here. And I'm just going to add that when I add this column together. So 1 plus 2 is 3, and then 3 plus 9 is 12. Now, when you don't have any more numbers to the left here, I can just simply write a multi-digit number into the answer. And the reason for that is because I'm still maintaining place value. I'm still having a 2 in the hundreds column, and this 1 is just pushed out into the thousands column. Because essentially, if there were more numbers over here, the 1 would have got carried over. But there are none, so it just comes straight down. So we end up with our answer of 1,219. And to think about this carrying action just a little bit more, when we look at the result of this column here, which was 4 tens plus 7 tens, really we got 11 tens, right? We got 11 tens, which essentially all we did was we broke it down into 100 plus 110. If I gave you 11 $10 bills, you would have $110. If I gave you a $100 bill and a $10 bill, you'd still have $110. So it's the same either way. So this is exactly what we did. We put 110 right here, and then we carried 100 into the next column to be added with the hundreds. Okay, for the next one we have 6,099 plus 15,763. And as I told you earlier, typically you're going to take the number with more digits and put that on top. So we'll take 15,763 and put that on top. We'll take 6,099 and we'll put that on the bottom. And let me just make this a little cleaner. So again, we're going to start with the digits in the ones column. 3 plus 9 is 12. 12 is too big to fit in the answer column. So I keep the rightmost digit, which is a 2, right? We think about 12. The rightmost digit is a 2. And then I carry the leftmost digit, which is a 1, into the next column. Now I add. 1 plus 6 is 7. 7 plus 9 is 16. So again, I have to carry. So I'm going to put a 6 down, right? Think about 16. The rightmost digit is a 6. And again, I'm going to be carrying a 1. And now I'm going to add. 1 plus 7 is 8. 8 plus 0 is still 8. And just keep moving on to the left. Now we have 5 plus 6, that's 11. So you think about 11, you have a 1 that's going to go into the answer column, the rightmost digit, and then you have a 1 that's going to get carried over into the next column. So now we add this column. 1 plus 1 is 2, and we just bring that down. So we get 21,862 as our answer. Hello and welcome to Pre-Algebra Lesson 8. And in this video, we're going to learn about subtracting whole numbers using a number line. So for the lesson objectives, we want to learn how to identify the parts of a subtraction problem. And we also want to learn how to subtract whole numbers using a number line. So what is subtraction? Well, subtraction is the mathematical operation that allows us to take away. The main idea behind subtraction is to find out how much is left over. So suppose you have 3 $1 bills and you go to a fast food chain and you spend $2 of your $3 on a hamburger. How much would you have left? So you can kind of picture these 3 $1 bills with 2 crossed out now because you've spent those. Well, you just have 1 left. And this is basically the subtraction problem. 3, which is what the amount you start with, minus 2, which is the amount you're going to spend or the amount that's going to be taken away. And that's going to be equal to 1, which is the amount that you're going to have left over after you've spent the money. So again, subtraction is the operation that allows us to take away. In the example, 2 was taken away from a starting amount of 3. Again, we started with $3. We spent 2. That's what's taken away. And then the result was 1. That's what we had left over. We just had a buck left. Okay, so to be more formal, let's give names to the parts of a subtraction problem. So we're going to start out with this called the menu end. Okay, the menu end. And this is the whole amount or starting value. So in the problem, 3 minus 2 equals 1. The whole amount or starting value is 3 because I started out with $3. So this is the menu end. This is the menu end. Then the next part of the subtraction problem is called the subtrahend. Okay, the subtrahend. So this is the amount being taken or subtracted away. So in the problem, 3 minus 2 equals 1. 2 is the subtrahend. This is the subtrahend. Okay, that's the amount that we took away to buy the hamburger. And then finally, we have the difference. Okay, the difference. This is the result of the subtraction operation, basically what we have left over. So 3 minus 2 equals 1. The 1 here, the result or what we have left over, is the difference. Okay, so let's just label these parts 2. Again, this is the subtrahend. And this is the minuend. Okay, let's look at a few examples. We want to name the parts of the following subtraction problems. So we have 13 minus 7 equals 6. So 13 is your minuend. Okay, this is the number from which another is subtracted from, or your starting amount, or the whole amount that you have, however you want to think about this. This number 13 is your minuend. Then we're subtracting away 7 from 13. 7 is what we're taking away, so this is the subtrahend. And then finally, 6 is the result of the subtraction operation here, and so it's going to be the difference. Okay, so 6 is the difference. And again, you can also think about the difference as just being the amount left over when you're finished performing the subtraction. I started with 13, that's my minuend. I took away 7, that's my subtrahend, and I have 6 left over after that operation, that's my difference. Okay, now we'll look at 8 minus 3 equals 5. The amount we're starting with, or your whole amount from which another is subtracted, is 8. That's the minuend. Then we have 3. That's what we're subtracting away. So 8 minus 3. Okay, we're taking away 3. That's the subtrahend. And then lastly, we have this 5 here. That's the result of our subtraction operation. We start with 8. We take away 3. The result is 5. So 5 is the difference. Okay, the next thing we want to talk about, if you remember in addition, we have something called the commutative property. And the commutative property tells us that we can add in any order that we'd like, and we don't change the sum. So in other words, 3 plus 9 is equal to 9 plus 3. Right? 3 plus 9 equals 12, 9 plus 3 equals 12. Changing the order around doesn't affect what's going on with my answer. Now, what I want to draw your attention to is that it's very important to note that the commutative property that is associated with addition does not work with subtraction. So in most cases, if you change the order of your subtraction, you're not going to get the same answer. So I have some examples of this. And I started out with the addition one, just to show you that it does work for addition. 3 plus 6 equals 9. 6 plus 3 equals 9. This works out. 6 minus 3 is 3. 3 minus 6 is negative 3. And we haven't covered negative numbers yet, or integers or anything. Just take my word for it, it's negative 3. So these two values are not the same. So the way that we subtract here made a difference. If I change the order, meaning I go from having 3 last to 3 first, I don't get the same result. Same thing over here. 9 minus 2 is 7. 2 minus 9 is negative 7. So changing the order did change the result. Then lastly, we have 7 minus 5 is not equal to 5 minus 7. 7 minus 5 is 2. 5 minus 7 is negative 2. So again, changing the order does change the result when you're subtracting in almost all the cases. There are some special cases where it's not, but we want to have things as a general rule. So as a general rule, when you're adding, you can change the order around as much as you want. As a general rule, when you're subtracting, you cannot do that. Okay, so now let's talk a little bit about subtracting whole numbers on the number line. This exercise will help us greatly when we start working with integers. So we already practiced adding whole numbers on a number line. Yeah, it was a trivial thing, but it's going to help us when we get to integers, and it's going to be the same thing for subtracting. We need to get a foundation going so that when we get to integers, things flow more smoothly. Okay, so now we want to subtract each using a number line. And to perform subtraction on a number line, it's essentially the same as performing addition on a number line. It's just a little bit of a change on the second step. So let's just learn through an example. We have 7 minus 4. The first thing you're going to do is you're going to start at the leftmost number on the number line. So if you recall from adding on a number line, that step is the same. You always start at the leftmost number. So that's going to be right here. That's 7 on the number line. Now, when we add, so in other words, if we're adding 4, we move to the right by 4 units on the number line. But now since we're subtracting 4, okay, since we're doing subtraction, we're just going to the left by 4 units. So the only thing that's changing is instead of going to the right, we're going to the left. Other than that, the procedure is the same. So we're subtracting 4. We're just going to go 1, 2, 3, 4 units to the left. So that's going to put us at 3. And obviously we know 7 minus 4 is 3. But it's just cool to do it on a number line. So this is our result. So we have 7 minus 4 equals 3. Okay, now we have 12 minus 5. So we're going to start out at the leftmost number. So we're starting out at 12 on the number line. That's right here. And then we're subtracting away 5. So we're going to move 5 units to the left. So I'm going to go 1, 2, 3, 4, 5 units to the left. And I end up at 7. And of course, we all know 12 minus 5 is 7. But we just did it on a number line. So 12 minus 5 equals 7. Okay, now we have 8 minus 7. So again, we're starting out at the leftmost number on the number line. So we're starting out at 8. That guy's right here. And we're subtracting away 7. So we're moving 7 units to the left. So we're going to go 1, 2, 3, 4, 5, 6, and then finally 7 units to the left. And we end up at 1. All right, we end up at 1. And of course, we know that 8 minus 7 is equal to 1. Okay, we'll look at one last problem. Overall, this is pretty simple, right? If you're adding on a number line, you start out at the leftmost number. You go to the right by the number of units you're adding. If you're subtracting on a number line, start at the leftmost number. You go to the left now by the number of units that you're subtracting away. So we have 5 minus 5. 5 minus 5. So that means I'm going to start out at 5 on the number line. That's right here. And then if I'm taking away 5, we know that we're going to end up at 0, right? Because a number minus itself is 0. So let's go 5 units to the left. 1, 2, 3, 4, and 5. Okay, so we end up at 0 right here. And 5 minus 5 equals 0. Hello and welcome to Pre-Algebra Lesson 9. And in this lesson, we're going to learn about vertical subtraction. So our lesson objectives for today would be to learn how to subtract multi-digit numbers. And also, we want to learn the borrowing procedure. So in a previous lesson, I taught you how to do vertical addition. And vertical addition is a convenient way to add multi-digit numbers together. And again, when I say multi-digit numbers, I mean numbers that are larger than 1 digit. So vertical subtraction is essentially the same thing. It's a convenient way to subtract multi-digit numbers. But there's some differences that we need to cover. So let's explain through an example here. The first step for vertical subtraction, we want to line up the subtraction problem vertically and by place value. So you'll recall with vertical addition, it's the same first step. So let's say that we have, 47 plus 13 for the addition problem. And let's say that we have 47 minus 13 for the subtraction problem. So here's the main thing that you need to understand. When we do addition, addition is commutative. So the order that we add in does not matter. So in other words, when I go through and I stack these numbers on top of each other, it doesn't matter what I put on the bottom and what I put on the top. So I can do 47 plus 13 like this, or I could do 13 plus 47 like this. Either way, I'm going to get the same answer. So we can go through and add. 7 plus 3 is 10. And we know we need to carry here. So the 1 goes into the next column. 1 plus 4 is 5. 5 plus 1 is 6. So I get 60. If I come over here, I'm going to get the same thing. 3 plus 7 is 10. Carry the 1. 1 plus 1 is 2. 2 plus 4 is 6. I get 60. Now with subtraction, we don't have the commutative property. So what goes on top and what goes on the bottom is going to matter. So you want to take the leftmost number for your subtraction problem. And remember, this is called the minuend. And you want to put that on top. So when we're stacking these numbers, that guy has to go on top. And then you want to take your subtrahend. That's 13 in this case. Your subtrahend. And that's the value that's being taken away or subtracted away. And you want to put that guy on the bottom. And again, notice how we're stacking the numbers. They have to be lined up by place value. So all the numbers in the ones place have to line up. All the values or the numbers in the tens place, okay, they have to line up as well. And if we had hundreds and thousands and so on and so forth, those would have to be lined up. So that's your first step. And again, you have to make sure that the correct number is on top and the correct number is on bottom. That way you get the right answer. Okay, for the second step, we want to draw a horizontal line directly underneath the bottom number, just like we did with vertical addition, and then place a minus symbol, okay, the minus symbol, to the left of the bottom number. So essentially, it's the same thing as when you're doing vertical addition. You're just putting a minus symbol in instead of a plus symbol. So we had 47 and we had 13 stacked on top of each other. So again, draw a horizontal line underneath the bottom number and put a minus symbol or a subtraction symbol to the left of the bottom number. And we're ready to move to the next step. So we have 47 minus 13 like that. And for step 3, we subtract in the ones column and place the result directly below the line, just like we did with vertical addition. So if I do 7 minus 3, that gives me 4, and I just put that directly below in the ones column. You just think about this as a ones column that just goes all the way down. Now, in the next step, we're just going to move to the left, just like we did in vertical addition. So in the next step, I would just move to the left, and I would say, okay, what is 4 minus 1? Well, that's 3. And then I've finished the problem. You just keep working right to left. So you start all the way in the rightmost column, and you just keep going to the left. So we end up with 34 as our answer for 47 minus 13. Okay, let's look at some examples now. So we're going to start out with 96 minus 35. So stack the numbers on top of each other. 96, 35. And remember, this 96 here, this is your minuend that's got to go on top. And then 35, that's your subtrahend that's got to go on the bottom. We'll throw our subtraction symbol out there and put our horizontal line underneath. And we're ready to subtract. Remember, we're going to start in the ones column, the rightmost column, and work our way to the left. So 6 minus 5 is 1. And then we go to the next column, the tens column, and we have 9 minus 3, and that's 6. So 96 minus 35 is 61. Let's look at 87 minus 23. Okay, we're going to stack these numbers on top of each other and make sure they're lined up by place value. So remember, 87, your minuend has to go on top. 23, the subtrahend, has to go on the bottom. So we're going to subtract beginning in the ones column. So we have 7 minus 3, that's 4. And then we work our way to the left. Now we're in the tens column. 8 minus 2, that's 6. So our answer here is 64. Okay, now we have 25,375 minus 10,164. Again, we're going to stack these numbers on top of each other. This number, the leftmost number, the 25,375, the minuend has to go on top. The subtrahend, 10,164, has to go on the bottom. Okay, so we're going to start on the ones column, and we're going to do 5 minus 4, that's 1. We're just going to work our way to the left. Now we're in the tens column. 7 minus 6, that's 1. Now we're in the hundreds column. 3 minus 1, that's 2. Now we're in the thousands column. 5 minus 0, that's 5. And now we're in the 10,000s column. 2 minus 1 is 1. So we end up with 15,211. So the examples that we've looked at so far are not very challenging at all. They're actually very, very simple. But in the next few examples, we're going to see some things that are going to kind of challenge us a little bit at first. So in many cases, the lower digit of a column is larger than the upper digit. When this occurs, we use a procedure called borrowing. And it's best for me to explain this through an example. So let's look at 43 minus 17. So we start the problem off just like we would any other. So we'd have 43 on top minus 17 on the bottom. And what happens is when we try to subtract in the ones column, we see that 3 is smaller than 7. So what happens when I try to do 3 minus 7? We haven't gotten to integers yet, so we don't know how to do this. Essentially, we only know how to subtract when the left number is bigger than the right number, right? When the minuend, or the amount that you're starting with, is larger than the subtrahend, or the amount you're trying to take away. So what we're going to do in this case is we're going to use this procedure called borrowing. Okay, we're going to borrow. And how this works is I go to the next digit to the left, and I'm going to borrow 1. Okay, so I'm going to cross this 4 out, and I'm going to subtract away 1, and that would give me 3. So now this 4 is now a 3. And I'm borrowing it, and I'm sending it over to the column to the right, and I just put a 1 in front of the digit in that column. So now this 3 is a 13, and I'm able to subtract. So I can say 13 minus 7 is 6, and then I just move to the column to the left, and I say 3 minus 1 is 2. So I end up with 26. Now, let me explain a little bit further as far as why this works. If we think about the numbers in terms of the place value of the digits involved, 43 is what? It's 40 plus 3. And 17 is 10 plus 7. So if we think about what we just did, when I crossed out this 4 and made it a 3, you think about this, I crossed this 4 out, and making it a 3, I basically made it a 30. Right? I made it a 30. And then I put a 1 in front of that 3. So if I put a 1 in front of that 3, it's a 13. So 30 plus 13 is still 43. I just changed the way it looked. Right? I didn't change the value of the number, so I didn't do anything illegal here. So now when you kind of look through the columns, you can see that, okay, I have 13 minus 7, that gives me 6, and I have 30 minus 10, that gives me 20, or a 2 basically because it's in the tens place, right? 2 groups of 10 is 20. So that's essentially what we're doing when we're borrowing. We're not changing the value of the number, we're just changing the way it looks temporarily so that we can perform the subtraction in that column. Okay, let's take a look at another one. So we have 512 minus 395. So 512 goes on top minus 395, which is on the bottom. And when we try to do our subtraction in the ones column, we have 2 minus 5. We know that 2 is the smaller number, so we need to borrow. So I'm going to go to the next column over to the left, and I'm going to take 1 away. So 1 minus 1 is 0. So now that's 0. And then I'm going to put a 1 in front of this digit 2. Okay, so I'm putting a 1 in front of that. I end up with a 12. So 12 minus 5 is 7. Now I have another problem because when I get to this column, I have a 0 and I'm trying to subtract away a 9. So I need to borrow again. So I'm going to the next column over, and I'm going to take 1 away from this. So 5 minus 1 is 4. And I'm going to put a 1 in front of this. So now this 0 becomes a 10. So then 10 minus 9 is 1. Okay, 10 minus 9 is 1. And then 4 minus 3 is 1. So we end up with 117. So again, let's look at these two numbers in expanded notation and see if we can figure out what we just did. So 512 is 500 plus 10 plus 2. 395 is 300 plus 90 plus 5. So basically when we started out, we rewrote the number by taking this 10 and sending it over here. So this became 0 and this became 12. Right? Just think about adding 10 to 2. So now I have 500 plus 12. That's still 512. Haven't changed the value of the number. So we did our subtraction. We did 12 minus 5. We got 7. But now when I went to the tens, I had a 0 here and I was trying to take away 90. So what I did was I went over to the hundreds place and I borrowed 100. So I took this and made it 400. Right? I subtracted away 100. And I sent it over here and I made this 100. So then 100 minus 90 gave me 10. Okay, gave me 10. And now I was just left with 400 minus 300, and that gave me 100. And so now if I look at this number, this is exactly what we got. 100 plus 10 plus 7, which is 117. So again, that's what borrowing is doing. It's just temporarily changing what these columns look like so that you can do your subtraction. But in order to really understand it, just go through as you're doing it for the first few times. Write the numbers in expanded notation and look at what you're actually doing. Okay, for the final problem, we have 190,005 minus 79,877. So we'll start out, again, stack the numbers on top of each other. 190,005 goes on top. 79,877 goes on the bottom. And Of course, when you start trying to subtract here, you notice that there's a problem. 5 minus 7, we need to borrow. But we'll notice when we look at our neighbor to the left, you have a 0 there. You can't borrow from that 0. So basically when this happens, you have to go to the left until you find a non-zero number. So we have to go all the way to this guy over here, to this 9, and borrow from that. But it's not as straightforward as you think. Take 1 away from the 9, you get 8. I have to send it to this guy here. Okay, I can't just send it express to the 5. So we got to go through this long, tedious process. So this 0 becomes a 10, and then I'm going to borrow from that. So this 10 will become a 9, and then this 0 will become a 10. Then this 10 will become a 9, and this 0 will become a 10. Then this 10 will become a 9, and this 5 will become a 15. So all that work just so I could subtract here. So now I can finally subtract in the ones column. 15 minus 7 is 8. We move to the left. This is now a 9. 9 minus 7 is 2. Move to the left. 9 minus 8 is 1. Move to the left. 9 minus 9 is 0. Move to the left. 8 minus 7 is 1. And then we have this 1 here. We're not subtracting anything away from it, so it just comes down. And we end up with 110,128 as our answer. So for one final time, let's write these numbers in expanded notation and see if we can figure out what happened. Scroll down a little bit and get a little room. So 190,005 is what? It's 100,000 plus 90,000 plus 5. And then our other number is 79,877, and that's going to be 70,000 plus 9,000 plus 800 plus 70 plus 7. Okay, now this isn't really lined up, so let me try to line this up for you. So 100,000 plus 90,000 plus, you'd have a blank spot here for the thousands place. You'd have a blank spot here for the hundreds place. You'd have a blank spot here for the tens place. And then finally, you'd have a 5 in the ones place. Okay, for this number, you'd put 70,000 here, plus 9,000, plus 800, plus 70, plus 7. So when we start our subtraction problem, we immediately see that 5 is smaller than 7. So we need to borrow. But when we look at our neighbors here to the left, they don't have anything that we can take. So we got to go all the way to the 10,000s place. So in the problem, if we go back up here, you remember we crossed this out and we subtracted away 1, we got 8. But that 8 is in the 10,000s place, so it's really 80,000. So if I cross this out, I'm subtracting away 10,000. I'm going to write this as 80,000 now. That's the new value. And I'm going to send 10,000 to my neighbor to the right. So now he has 10,000 there. And I haven't changed the value of the number because 100,000 plus 80,000 plus 10,000 plus 5 is still 190,005. Now I need to keep going until I get to that 5 there. So I'm going to keep borrowing. So I'm going to cross this out. And basically, since I'm in the thousands place now, I'm going to take 1,000 away. So this is going to become 9,000. So now I have 9,000. And I'm going to send that 1,000 that I took away over here. So now this is 1,000. And I need to keep doing this. So I'm going to take, now I'm in the hundreds place, I'm going to take 100 away. So this is going to become 900. And I'm going to throw 100 over here in the tens place. Now I'm going to do it one last time so that I can reach this 5 over here. So I'm in the tens place, so I'm going to take 10 away. So this will become 90. And this will become 5 plus 10 or 15. Okay, think about that as 15. Now when we do our subtraction, 15 minus 7 is 8. 90 minus 70 is 20. 900 minus 800 is 100. 9,000 minus 9,000 is 0. And 80,000 minus 70,000 is 10,000. And this, I'm not subtracting anything away from it, so 100,000 is going to stay there. So when we look at this right here, this is 100,000 plus 10,000 plus 100 plus 20 plus 8, or 110,128, which is exactly what we got right here. Hello and welcome to Pre-Algebra Lesson 10. And in this video, we're going to learn about the properties of multiplication. So for the lesson objectives, we want to learn the basic parts of a multiplication problem. We want to learn the commutative and associative property of multiplication. We want to learn about the identity property of 1, the multiplication property of 0, and the distributive property of multiplication. Okay, so I want to start out the lesson by just briefly thinking about what's going on when we're multiplying whole numbers together. So back in elementary school, when you first started thinking about multiplying whole numbers, you probably started out with learning the times table, and your teacher probably at the same time put something like this up on the board. So here we have 7 plus 7 plus 7 plus 7 is the same as 4 times 7. And essentially, if we look at an addition problem where the same whole number is being added, so in this case, that whole number is 7, right? We have 7 plus 7 plus 7 plus 7. We can use multiplication as a shortcut. So instead of writing this out each time and going through and saying, okay, well, 7 plus 7 is 14. 14 plus 7 is 21. 21 plus 7 is 28. We can do it more quickly with this multiplication. We have 4 groups, right? We have 1, 2, 3, 4. 4 groups of 7. So we use that fact to say that, okay, this is 4 times 7, or 28. So it's a more quick way to perform a repeated addition. If we look at this example here, we have 9 plus 9 plus 9 is the same as 3 times 9, right? Because I have 1, 2, 3 groups of 9. So we know that 3 times 9 is 27. And if we went back and did the addition, we get the same result. 9 plus 9 is 18. 18 plus 9 is 27. Okay, let's look at 2 quick problems. We want to rewrite each as a multiplication problem and solve. So what I have here is I have 2 plus 2 plus 2 plus 2 plus 2. So essentially I have what? I have 1, 2, 3, 4, 5 groups of 2. So this would represent 5 times 2 if we do it using multiplication. And we know that 5 times 2 is 10. And if we go back and verify through addition, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, and finally 8 plus 2 is in fact 10. Okay, now we have 4 plus 4 plus 4 plus 4 plus 4 plus 4. So if I count these out, I have 1, 2, 3, 4, 5, 6 groups of 4. So this represents 6 times 4, and we know that that's equal to 24. And again, we can go through and verify this through addition. 4 plus 4 is 8. 8 plus 4 is 12. 12 plus 4 is 16. 16 plus 4 is 20. And then lastly, 20 plus 4 is 24. Okay, now let's talk about a little bit of basic terminology. So numbers being multiplied together are called factors. Okay, they're called factors. Then the result of the multiplication is called the product. So if we look at 6 times 5 equals 30, 6 and 5 here are being multiplied together. So those are going to be the factors. And then 30 is the result of the multiplication process. So this is the product. Okay, the product. And a lot of times you'll hear people say 30 is the product of 6 and 5. Okay, now we have 9 times 7 times 2 equals 126. So these three numbers here are the factors for this problem. 9, 7, and 2, that's what we're multiplying together. And then 126 is the result of the multiplication. So this is the product. Okay, the product. Okay, now let's talk about some properties of multiplication. And a lot of these are extremely straightforward. Some of them you've used before, you just might not have known the official name for them. So we're going to start out with the commutative property of multiplication. And essentially this just tells us that we can multiply in any order and not change the product. And we've already seen the commutative property of addition. Remember, we could add in any order and it didn't change the sum. Here, again, we can multiply in any order. We can multiply in any order and not change the product. So if you have 3 times 6, which 3 in this case is first, 6 in this case is, you can think of as last, we put this as equal to or the same as 6 going first and 3 going last. Doesn't matter how you multiply. You're going to get the same answer either way. 3 times 6 is 18, and 6 times 3 is 18 as well. Okay, as another example of the commutative property, we have 12 times 9 equals 9 times 12. And again, you can prove this to yourself. If you multiply 12 times 9, you get 108. If you multiply 9 times 12, again, you get 108. So changing the order does not affect your product. Okay, let's look at an example real quick where 3 factors are involved. So we have 7 times 5 times 4 is equal to 5 times 7 times 4, and that's also equal to 4 times 7 times 5. So the same 3 numbers are being multiplied, 7, 5, and 4. We're just changing the order around. And no matter how you do this, you'll get the same answer. 7 times 5 times 4, 7 times 5 is 35, 35 times 4 is 140. Now if I do it this way, 5 times 7 times 4, well, we already know that 5 times 7 and 7 times 5 are the same, so we know we would get 5 times 7 is 35, and then 35 times 4 is 140. And then if I do it this way, 4 times 7 times 5, well, I could do 4 times 7, that's 28, and then multiply times 5, that's also 140. So again, it's very important for you to understand that when you're doing multiplication, and there's only multiplication involved, you can do it however you want. The order is never going to matter. It's never going to change your end result. Okay, now let's talk about the associative property of multiplication. So with this property, we can group the multiplication of 3 or more numbers in any order without changing the product. Notice that where we have 6 times 3 times 1, we have parentheses here around 6 times 3. And we're saying this is equal to or the same as 6 times, and now I have parentheses around 3 times 1. So when we say grouping, we're talking about putting parentheses around different numbers. So if you just have multiplication involved, you can put parentheses around different numbers or take the parentheses away. It's not going to matter at all. You will get the same answer. So if I look at 6 times 3 times 1, where 6 times 3 is inside of parentheses, we would do this first. And I know we haven't gone through order of operations yet, but whenever you have operations inside of parentheses, you start with that. So we would do this first. 6 times 3 is 18. Then 18 times 1 is 18. And just thinking about this over here, now we have 3 times 1 inside of parentheses. So we'd start with that first. So you would have 6 times the result of this, which is 3, right? 3 times 1 is 3. And 6 times 3 is 18 as well. So either way you do it, you end up with 18 as the answer. All right, let's take a look at a few examples here. We have 4 times 2 inside of parentheses, then times 8. And we're saying this is equal to 4 times, and then we have 2 times 8 inside of parentheses. So again, you want to start out with what's inside of parentheses first. So on the left here, we have 4 times 2 inside of parentheses. That gives us 8. So we would have 8 times 8, and that equals 64. Over here on the right, I have 2 times 8 inside of parentheses. So I'd do that first. So we would have 4 times 2 times 8 is 16, and 4 times 16 is also 64. So again, changing what we had parentheses around or changing our grouping did not change the product. It didn't matter that we switched what we had parentheses around. We got 64 either way. All right, let's look at one last problem. We have 9 times, and then we have 7 times 5 inside of parentheses. And we're saying this is equal to, here we have 9 times 7 inside of parentheses, then times 5. So again, start with the parentheses. On the left, I have 7 times 5 inside of parentheses. So we would have 9 times 35. And 9 times 35 is 315. On the right, I have 9 times 7 inside of parentheses, so I would do that first. 9 times 7 is 63. And then times 5 is 315 as well. So again, just to kind of wrap this up, I know this is a very easy topic, but essentially, when you think about the associative property of multiplication, it's really just telling you that you can put parentheses around whatever numbers you want when you're multiplying 3 or more numbers. It will not, in any case, change the product or the result that you get from your multiplication. Okay, now we're going to talk about 2 very simple properties. The first one is going to be called the identity property of 1, And then we're going to talk about the multiplication property of 0. So the identity property of 1 states that any number multiplied by 1 remains unchanged. And I think we all know this fact, because when you think about the times tables, it's always about, okay, 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, 4 times 1 is 4, 5 times 1 is 5. So you kind of learn that fact immediately, because that's the easiest one to do. So when we look at 15 times 1, we know we just get 15. Or if we look at kind of some bigger numbers, what's 97 times 1? Well, it's just 97. What's 3,866,151 times 1? Well, it's just 3,866,151. So a very easy property, and a lot of times, kind of in a pre-algebra test when you're first starting out, they'll throw this in there just to kind of trip you up. Oh, hey, this is a big number. How am I going to do this multiplication without a calculator? Well, you use the simple fact that a number times 1 is just itself. Okay, so probably just as easy, the multiplication property of 0 tells us that any number multiplied by 0 gives us a result of 0. So when we start out with 30 times 0, what's the result? It's 0. When we think about 25 times 0, well, the result is 0. When we think about 2,577,313 times 0, well, the result is 0. And a lot of times they'll put this question on a test, but they won't put it straightforward like that. They'll give you these numbers that are being multiplied together. So let's say something like 14 times 10 times 5 times 0 times 30. And a lot of students will see this and they'll go, oh, how am I going to do that without a calculator? Many of them could do it, but it would just take a long time. Well, you use the fact that 0 times any number is always 0. It doesn't matter what the result of the multiplication is through here, because whatever number that you get as a result, when you multiply it by 0, you get 0. Then when you multiply 0 times 30, you get 0. So when you see something like this where you have a lot of numbers being multiplied together and there's only multiplication involved, and you have 0 as a factor, you know that the result of that problem is going to be 0. Okay, now let's talk about a very important property. The distributive property of multiplication tells us that multiplication is distributive over addition or subtraction. And I have as a side note here that we use this property constantly in algebra. So now is a great time to learn and understand this property, because when you get to algebra, you're literally going to use it all the time. Okay, so I'm going to explain the distributive property by looking at a few examples. So we're going to start out with 4 times, and then we have 3 plus 6 inside of a set of parentheses, or we can think about this as 4 times the quantity, okay, the quantity 3 plus 6. One of the things I'm going to draw your attention to, and this is kind of a side note, is that up to this point, most of you have only used this to imply multiplication. So if I said, what is 4 times 3? You'd probably write that problem out like this, and you'd solve it and say, okay, 4 times 3 is 12. As we move higher in math, this symbol is going to go away in terms of multiplication. You won't use that anymore. And there's a variety of different ways that we can imply multiplication, and we'll kind of get to those as we move on. But for right now, I just need you to know that when we put a number outside of parentheses, it implies multiplication. So I could write 4 times 3 like this. Okay, I have 4, and it's directly next to a 3 that's inside of parentheses. So that's why I say 4 times this quantity 3 plus 6, because 4 is next to that set of parentheses. Okay, now let's talk a little bit about the distributive property. And before I even get into that, let's think about solving this problem without using distributive property. So I know we haven't done the order of operations yet, but that tells us before we do anything else to perform operations inside of parentheses. So we have 3 plus 6 inside of parentheses. 3 plus 6 is 9. So this would be 4 times 9, or 36. Now when we use the distributive property, we have an alternative way to get this answer. So 4 times this quantity 3 plus 6. Essentially what we're going to do is we're going to take this 4 and we're going to distribute it to each number inside of the parentheses. So we would say 4 times 3 plus, okay, plus 4 times 6. 4 times 6. So you have to remember to multiply by each number inside of the parentheses, and everywhere there's a plus symbol, or in some cases it's going to be a minus symbol because this works with subtraction too, you have to write that. Okay, you can't skip that over. Now, if we go through and we solve this, we're going to do the multiplication first because that's what the order of operations tells us. So we're going to treat these as separate problems before we add. So 4 times 3 is 12, then plus 4 times 6, which is 24. So 12 plus 24 is also 36. So either way, we're getting the same result. Okay, 36 either way. Now I'm going to erase all of this real quick, and we're just going to rewrite this, and then I'm going to kind of do this a long way. So 4 times 3 plus 4 times 6, and you can leave it like this or you can put parentheses around this like this. It won't change your answer if you know the order of operations. I just put the parentheses around it so that you know to do 4 times 3 separately from 4 times 6. I don't want you to get confused at this point. Now, if I think about the addition problem that we did earlier, 9 plus 9 plus 9. This is 3 groups of 9, so we said this is 3 times 9. If I apply that same logic here, I have 4 groups. I have 4 groups of 3 plus 6. So what does this translate to? 3 plus 6 plus 3 plus 6 plus 3 plus 6 plus 3 plus 6. Now, I know that the associative property and the commutative property allow me to reorder and regroup this addition however I want. So what I'm going to do is I'm going to write inside of parentheses 3 plus 3 plus 3 plus 3. I have 1, 2, 3, 4 of those. Then plus, inside of another set of parentheses, I'm going to put the 6's. So I have 1, 2, 3, 4 of those. So 6 plus 6 plus 6 plus 6. Now, if I look at it this way, it is clear to me how I arrived at this result. I have 1, 2, 3, 4 groups of 3, which is known as 4 times 3. I have 1, 2, 3, 4 groups of 6, which is 4 times 6. So you can see that this directly matches this. Using the distributive property was just a shorter way to get there, right? Because I know in the end I'm going to have 4 groups of 3, and I'm going to add to that 4 groups of 6. All right, let's look at another one, and we won't go through that long, tedious process again. We have 7 times the quantity 9 plus 2. So we're going to do this 2 different ways. We're going to do it the first way where we do 9 plus 2 first, because that's what's inside of parentheses. So this is 7 times 11, and that's 77. And then let's do it using the distributive property. So remember, I have 7 groups of 9, or 7 times 9, plus I have 7 groups of 2, or 7 times 2. And I'm going to put parentheses around each here so we know to do that first before we add. And again, you won't need that, but we haven't done the order of operations yet, so I don't want to confuse you. So 7 times 9 is 63. And then plus 7 times 2, that's 14. And so 63 plus 14 is 77. So either way, using distributive property or adding what's inside of parentheses first, we get 77. Okay, now let's look at one that involves subtraction, because this does also work with subtraction. So we have 8 times the quantity 4 minus 3. So working inside of parentheses first, I'd get 1. 4 minus 3 is 1. So we'd have 8 times 1, and that just equals 8. If I use the distributive property, again, I want to distribute this. So 8 times 4, 8 times 4, and then we're subtracting 8 times 3. 8 times 3. So again, I'm going to put parentheses around the multiplication problem so that you don't get confused. All right, so 8 times 4 is 32. And then we're subtracting away 8 times 3, which is 24. And 32 minus 24 is 8. So again, either way, we get the same result. Okay, let's take a look at one last problem. So we have 5 times the quantity 9 minus 4. again, doing this where we do 9 minus 4 first, 9 minus 4 is 5. You'd have 5 times 5, that is 25. Using the distributive property, we're going to distribute the 5, so 5 times 9, 5 times 9, then subtract away 5 times 4, 5 times 4. And again, I am going to put these multiplication operations inside of parentheses, just so that you don't get confused. And when we get to the order of operations, which will be a few lessons from now, you'll learn that you need to perform multiplication before subtraction. But for right now, we know that we got to perform operations inside of parentheses first. So let's just put the parentheses around it and work with that rule. So 5 times 9 is 45. Then minus 5 times 4, that's 20. And then we do this subtraction, 45 minus 20 is 25. So again, either way, we get the same result, either by doing what's inside of the parentheses first, or by using our distributive property, where we distribute our multiplication to each number inside of the parentheses. Hello and welcome to Pre-Algebra Lesson 11. And in this video, we're going to learn about vertical multiplication. So for the lesson objective, we want to learn how to multiply multi-digit numbers together. Okay, so up to this lesson, we have reviewed how to do addition of whole numbers and how to do subtraction of whole numbers. And we saw that when we needed to add multi-digit numbers or when we needed to subtract multi-digit numbers, we did it in a vertical format. Now, the same is going to be true when we think about multiplying whole numbers. Now, before we dig into that, I just want to make you aware that in order to be successful with vertical multiplication, you have to, at minimum, know your times tables. And those are the tables that you learned back in elementary school where you memorized, 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, so on and so forth. You need to at least know up through 9 times 9. So if you haven't memorized that, you probably need to go back, make some flashcards, and memorize that so that you can be successful with vertical multiplication. So essentially, you can think about it this way. What do we do when we want to multiply large numbers together? Are we really expected to memorize the multiplication for every number that we may come across? Well, no, of course not. When we multiply multi-digit numbers together, we use a process called vertical multiplication. All right, so I prefer to teach through examples, so let's start out by just looking at 26 times 6. Now, with vertical multiplication, it's going to be the same as vertical addition or vertical subtraction, where we want to stack the numbers on top of each other and line them up by place value. Now, you recall with addition, it didn't matter what went on the top and what went on the bottom, but it was easier, or I would say more common also, to put the number with more digits on top and the number with fewer digits on the bottom. That's going to be the same thing with multiplication. Multiplication is commutative. I can do 26 times 6, or I can do 6 times 26. I get the same answer. It will make your life easier if you take the number with more digits, which in this case is 26, and you put it on top. So I'm going to put 26 on top, and I'm going to put 6 on the bottom. Okay. Now, just like with vertical addition, we want to draw a horizontal line underneath the bottom number, and we want to put an operator symbol, which in this case is the multiplication symbol, out to the left of the bottom number. So performing this operation is very, very simple, and once you've practiced it enough, it'll be very, very easy for you. Okay, so to begin our vertical multiplication, we're going to start with the rightmost digit of the bottom number, and we're going to multiply by the rightmost digit of the top number, and we're going to continue working right to left. So we would begin by doing 6 times 6, and we know that equals 36, but 36 is too big to put in the ones place for the answer, so we're going to do a thing called carrying, which is similar to what we did with addition, but with a slight twist. So this part is the same. You take the rightmost digit, which is a 6, and you write it into the answer column. So I'm going to write a 6 right there. I'm going to then take the left digit, which is a 3, and I'm going to write that in the next column to the left. Okay, so it's going in the tens column. If you think about 36, again, thinking about place value, this is 30 plus 6. So all I've done is said that, hey, we have 6 ones, and I take 3 tens and I put it into the tens column. So that's why that's a 3 there. Again, that's 3 tens. Now, it's important to understand that that's 3 tens. This is 30, because that 30 is going to be added to the result of the next multiplication that we do. It's not going to be multiplied. We will simply add it on to the answer that we get. So now we're going to move to the left, and we're going to do 6 times 2. So 6 times 2. And once we have our result, we're going to tack that 3 on. So plus 3. Okay, so 6 times 2 plus 3. So 6 times 2 is 12. And then if we add 3 to that, we get 15. We get 15. So we're going to write that into our answer. We would write a 5. And normally we'd carry a 1, but there's nothing else over here. So that 1 can just be written right there. So we get an answer of 156. And really, it's just that simple. So if I think about 6 times, I'm going to break 26 up into 20 plus 6. So if I think about this using the distributive property, I'd have 6 times 20, 6 times 20, then plus I'd have 6 times 6, 6 times 6. This right here is exactly what we did here, and I'm going to show you that in a second. So I'm going to use some parentheses here to separate my multiplication operations from this addition. And you normally do not have to do that, but we at this point have not studied the order of operations. So I want it to be clear that we're going to do 6 times 20, and then 6 times 6, and then add the results. I don't want you to get confused on what operations we're doing. So 6 times 20 is 120, plus 6 times 6, that's 36. And when we add here, we get 156, which is the same thing that we got there. So looking at this, we can basically see that this over here, this vertical multiplication, is just a condensed version of the distributive property. That's all it is. I started out by doing 6 times 6. That's right here. 6 times 6 gave me 36. Then I did 6 times 20. It looks like 6 times 2, but that 2 is in the tens place, so it's really a 20. So I did 6 times 20, and that gave me 120. Now, I added 120 and 36, and I got 156. The only thing that's a little different here is we had to carry a 3 because we couldn't fit the 3 in the ones place. But essentially all I did was I said 6 times 20 is 120, plus this 3 here, which was really a 30, plus the 6, which was the number from the ones place when we did 6 times 6, right? That 36 right there. So plus 6, and that still gives us 156. So just letting you see this in a different light. Essentially, the vertical multiplication process that we use is just a condensed version of the distributive property. That's all it is. Okay, let's look at another one. So we're going to look at 613 times 5. So again, I'm going to take 613, and I'm going to put that on top because it has more digits. And then I'm going to put 5 on the bottom. And we multiply from right to left. So I start out with this digit on the right, and soon you'll have digits over here too. So you start out on the right, and you multiply by the rightmost digit of that top number. So we're doing 3 times 5. So 3 times 5 equals 15. So I'm going to take the 5 and put it down, and then I'm going to carry this 1. Now remember, I'm not going to multiply the 1. I'm going to only use that 1 once I'm done with the multiplication. So now I'm going to multiply 5 times the 1 there. So 5 times 1. And then when I'm done with that, I'm going to add this 1. I'm going to add that 1. So 5 times 1 is 5. Then plus 1 is 6. Okay. And again, think about what you're saying here. This 5 has a value of 5. This 1 has a value of 10 because it's in the tens place. So 5 times 10 is 50. Then I'm adding another 10. That's a 1 in the tens place. Then I'm adding another 10 to get to 60. So I have a 6 that's in the tens place. That's a 60. So that's what we just did. Now the last thing I'm going to do is I'm going to multiply 5 times 6. And that gives me 30. 5 times 6 equals 30. Now normally I'd have to put the 0 down and carry the 3. But there's nothing else over here. So I can just write that 3 there. I end up with 3065 as my answer. All right, for the next problem, we have 1,752 times 8. Again, I'm going to take this number here, this 1,752, and I'm going to put that on top, and I'm going to put 8 on the bottom. Again, you could reverse that if you chose to. I just find this to be a little easier. So we're going to begin by taking the rightmost digit of the bottom number, which in this case it's just an 8, so that's all there is. and multiplying that by the rightmost digit of the top number. So we're going to do 2 times 8 to begin, and that is 16. So for 16, we're going to need a carry. So I put a 6 down, and I carry a 1 into the next column. And remember, that's not going to be multiplied. That's going to be added after we do our multiplication. So we're working our way left. Now we're multiplying 8 times 5. So 8 times 5. And then once we're done with that, we're going to add this 1 in. We're going to add this 1 in. We're basically saying, hey, whatever you get, add 10 to that, because that 1's in the tens place. Add 10 to that. All right, so 8 times 5 is 40. Then plus 1 is 41. So I need to carry again. I'm going to take the 1, the rightmost digit, and I'm going to write that there. And I'm going to carry the 4, the leftmost digit, into the next column. Now we're ready to multiply in the next column. 8 times 7 is what we're doing next. So we'd have 8 times 7, then plus what we carried over. That 4 is in the hundreds place, so I'm saying, hey, whatever you get for the result here, I want you to add 400 to it. Okay? So I'm just writing this as a 4 because it's in the hundreds place. So 8 times 7 is 56, plus 4 is 60. Again, we need to carry. So I'm going to take the 0, I'm going to put that in the answer column, and I'm going to carry the 6 into the next column to the left. And we have one more multiplication left to do. Okay, so now we want to do 8 times 1. So 8 times 1. And we're going to add to that the 6 that we carried over. So again, whatever we get for this, we're adding 6 more. And that 6 is in the thousands place, so we're basically tacking on another 6,000 to that answer. So 8 times 1 is 8, then plus 6, it's 14. Now, because there's no more numbers to the left, I can just write 14 into my answer. So we get 14,016 as our result. All right, let's take a look at another easy one. So we have 15,319 times 7. And again, I put the number with more digits on top, the number with fewer digits on the bottom. And let's just crank this out. We're going to start at the rightmost digit. In this case, it's just a 7 of the bottom number. We're going to multiply it by the rightmost digit of the top number, and we're working our way to the left. So 7 times 9 is 63. So I would put a 3 down, and I would carry a 6 into the next column. Next, I would do 7 times 1. 7 times 1 is 7, then plus 6 is 13. So I'd put a 3 down, and I'd carry a 1. Then I'd have 7 times 3, that's 21. Then plus 1, that's 22. So I'd put a 2 down and carry a 2. Now I have 7 times 5, that's 35. Then plus 2, that's 37. So I'd put a 7 down and I'd carry a 3. And lastly, I have 7 times 1, that's 7. Then plus 3, that's 10. So I just write a 10 here. And we end up with 107,233. Okay, so up to this point, it's been pretty easy. And the reason for that is the number on the bottom has been a single-digit number. When we start multiplying a multi-digit number by another multi-digit number, the work gets more tedious. So let's start out by thinking about 315 times 12. So again, I'm going to write the number with more digits on top and the number with fewer digits on the bottom. And again, I want to start out at the rightmost digit of the bottom number and multiply it by the rightmost digit of the top number. So 2 times 5 would give me 10. Now, I'm going to put a 0 down, and I'm going to carry a 1. Next, I'm moving to the left. So I'm doing 2 times 1. So 2 times 1 is 2. Then add 1, so that's 3. Okay, working my way to the left. Now I have 2 times 3. 2 times 3 is 6. So the result here is 630. But I'm not done. Okay, I'm not done. I still have this other number over here to the left. And there's something that you have to do when that occurs. If you move to the left to multiply, you have to move to the left when you start your answer. So we're going on a whole nother row here, a whole nother row, and we're starting right here, okay, right here. And the reason we're doing that is because this 1 is not a 1. It's actually a 10, because again, it's in the tens place. So what I'm doing is I'm multiplying 10 times 5, and I'm getting 50. So I would write 50 by putting a 5 in the tens place, okay, by putting a 5 in the tens place. If I was to just multiply 1 times 5 and put 5 here, I didn't get the right answer because this isn't a 1, it's a 10. So I really need to do 10 times 5. So to correct for that, we just move 1 place to the left and we start our answer in the tens place. So let's begin there. So we're going to do 1 times 5. 1 times 5, as I just said, is 5. Now we move to the left. I'm going to do 1 times 1, and that's 1. And we move to the left one final time. We're going to do 1 times 3, and 1 times 3 is 3. Now you might say, what are we going to do now? Well, essentially, this 630 and this, what looks like 315, it's really 3,150 because of where it's positioned. Those are called partial products, okay? Partial products. What we actually have to do is we have to find the sum of these two rows to get the product for 315 times 12. This 0 here can either come down or you can write a 0 in. It doesn't really matter. So 0 plus 0 is 0. Then 3 plus 5 is 8. Then 6 plus 1 is 7. And then you can just bring that 3 down to get 3,780. So again, if we want to just think about this a little further, again, use the distributive property. Take this number 315 and multiply it by 10 plus 2, that quantity. Again, this is 12. I just broke it up. So doing this, we'd have 315 times 10, 315 times 10, plus 315 times 2. 315 times 2. And that's exactly what we just did here. We did the rightmost digit of this bottom number, 2 times 315. The result of that was 630. So if I think about this, I would have plus 630 over here. And we also did 315 times 10. Because this 1 is in the tens place, I multiplied 10 times 315, and that gave us 3,150. 3,150. So then we did some addition, just like we did over here. 3,150 plus 630, which gives us 3,780. Okay, let's try another one. So we have 765 times 23. So 765, I'm going to put that on top, times 23. I'm going to put that on the bottom. So again, we start out at the rightmost digit of the bottom number, and we multiply it by the rightmost digit of the top number, and we're just going to work left. So 3 times 5 is 15. Put a 5 down, carry a 1. 3 times 6 is 18, plus the 1 that we carried is 19. I'm going to put a 9 down and carry the 1. 3 times 7 is 21, plus the 1 that we carried is 22. And again, I can just write 22 because there's no more numbers out here. Now, we're going to the left in the bottom number. We have to remember to start our answer to the left right here. Because again, this isn't a 2 times 5, this is a 20 times 5. So I've got to start my answer right there. So then 2 times 5 is 10. So I'm going to put a 0 down, and I'm going to carry a 1. 2 times 6 is 12, plus the 1 I carried is 13. Put a 3 down, carry a 1. 2 times 7 is 14, plus 1 is 15. And because I don't have any more numbers out here, I can just write 15. Now, really, because of where this 0 starts, this number is 15,300. I can put a 0 in there if I want, or I can leave it out. It doesn't really matter. We're going to do some addition. So we add these two partial products up. Again, 2,295 is a result of doing 3 times 765. And then 15,300 is a result of doing 20. Again, that 2 is in the tens place, so it's a 20 times 765. So we find the sum here. 5 plus 0 is 5. 9 plus 0 is 9. 2 plus 3 is 5. 2 plus 5 is 7. And then this 1 can just come down. And we end up with 17,595. Okay, let's look at one final problem. And as your numbers get larger, your work doesn't get harder, it gets more tedious. And you have to pay very close attention to what you're doing because it becomes very easy to make a mistake, especially if you're on like your 11th or 12th problem and you're just exhausted. You'll start making these mental mistakes. So you have to pay close attention to what you're doing. Okay, so 212,050 times 1,075. I'm going to take this number, 212,050, and I'm going to put that on top. And I'm going to take 1,075, and I'm going to put that on the bottom. Okay, so again, we start out the rightmost digit of the bottom number times the rightmost digit of the top number, and we're just working our way to the left. So we're going to have 5 times 0. So 5 times 0 is 0. Then we're going to have 5 times 5. 5 times 5 is 25. So I'm putting a 5 down, and I am carrying a 2 into the next column. Now I have 5 times 0. That is 0, plus 2 is 2. Now I have 5 times 2. That is 10. So I'm going to put a 0 down, and I'm going to carry a 1. Now I have 5 times 1. That's 5, plus 1 is 6. Lastly, I have 5 times 2. That's 10. No more numbers out here, so I can just write that in. I'll go through and put some commas. So that's 1,060,250. And that's basically the result of 5 times 212,050. Okay, now we're moving to the left. So what happens when I move to the left? I've got to move to the left where I start my answer. Again, this is not a 7, it's a 70. Okay, it's a 70. So we're going to start out with 7 times 0. 7 times 0 is 0. 7 times 5 is 35. So I put a 5 down, I carry a 3. 7 times 0 is 0, plus 3 is 3. Then 7 times 2 is 14. So I'm going to put a 4 down, and I'm going to carry a 1. Now I have 7 times 1, that's 7, plus 1 is 8. And then lastly, I have 7 times 2, and that is 14. Okay, put in the commas. So I get 14,843,500. You might be saying, well, there's no 0 over here. Well, because I started this over here, there's really a 0 here. There's really a 0 there. But when we add, we don't have to put the 0 in because this can come just straight down and you're going to get the same answer. So I'm going to go ahead and just write a 0 there just so it's not confusing for you. Okay, so now we're going to continue, and we're moving left again. So I'm moving left, and when I do that, I've got to move left. So I'm not going to start in the tens anymore. I'm going to have to start in the hundreds. I'm going to have to start in the hundreds. And the reason for that is I'm starting in the hundreds here. So a lot of people like to just put the zeros in. You can do that and start your answer there. Or again, just as I told you, you can leave it blank. Let's go ahead and put the zeros in so that you're not confused. All right, so we're going to start with 0 times 0. That is 0. 0 times 5. That is 0. 0 times 0. That is 0. So you're starting to notice something. If you have a 0 and you're doing your multiplication, this whole row here will be 0. So essentially, I'm just going to include 1 0 there just so I can maintain my place. I don't really need to write anything else because if I add 0 when I'm doing the addition, it's not going to change the value of the number. So I'm just going to move to the left, and look at this 1 here. So now I've got to start my answer here in the thousands place. Okay, I've moved all the way to the thousands place. Notice how this 1 is in the thousands place. Okay, let's start. So we have 1 times 0, that's 0. We have 1 times 5, that's 5. We have 1 times 0, that's 0. We have 1 times 2, that's 2. We have 1 times 1, that's 1. And we have 1 times 2, that's 2. And another cool trick you can think about is if you're multiplying 1 times this, it's just going to be itself. Remember, 1 times anything leaves it unchanged. So I could have just wrote 212,050 and been done with it. As long as I know where to start, that's the important part. So if I want to, I can go ahead and write 3 zeros here, just so that we don't get confused. Okay, so we're going to go ahead and add. Let me make these zeros a little better so that they line up. So I'm going to come straight down. I have a 0 everywhere, and I can put zeros in here if I want. It doesn't matter. This is just 0 in the end. So coming straight down, I have a 0. Then I have 5 plus 0 plus 0 plus 0, that's 5. Then I have 2 plus 5, that's 7. Then plus 0, that's 7. Then I have 0 plus 3 plus 0, that's 3. Then I have 6 plus 4, that's 10. plus 0 is still 10, plus 5 is 15. So put a 5 down, carry the 1. Now we have 1 plus 0, which is 1, plus 8, which is 9, plus 0, which is still 9. Then I have 1 plus 4, which is 5, plus 0, which is still 5, plus 2, which is 7. Then I have 1 plus 0, which is 1, plus 1, which is 2, and then I can just bring this 2 down, and I end up with 227,953,750. Hello and welcome to Pre-Algebra Lesson 12. And in this video, we're going to learn about multiplication with trailing zeros. So our lesson objective is just to learn how to multiply numbers with trailing zeros. And you might be asking yourself, what in the world is a trailing zero? Well, a trailing zero is just a zero at the end of the number, or you might say trailing zeros if there's multiple zeros at the end of a number. So let's take the number 600. 600 has 2 zeros at the very end of it, so this number has 2 trailing zeros. Or you could look at the number 17,000. This number has 3 zeros at the end of it, so it has 3 trailing zeros. Where people get confused is you might have a number like, I don't know, let's say 104,030. This number has 3 zeros in it, but they're not all trailing zeros. You're only looking at zeros at the end of the number. It can't be interrupted by something that's not zero. So this one right here at the very end, that's a trailing zero. But because there's a 3 here, you can't say that this is a trailing zero also. Yeah, it's close to the end of the number, but it's not at the end. It's interrupted by this 3 here. So this number would have 1 trailing zero. Let's think a little bit about a simple multiplication fact that you might not have ever thought of. When you multiply, let's say something like 5 times 10, we know that this is 50. But another way to attain this result is to multiply the non-zero parts, so 5 times 1, that would give you 5, and then just attach the trailing zero to the end of the result. So in other words, I can do 5 times 1, and then I can attach a 0 to the end, that would give me 50, and I would have the result for 5 times 10. And this works no matter how large your numbers are. Let's say I would have said, what is 5 times 100? Well, now I would do 5 times 1, that's 5, and then I would attach 2 zeros to the end. 2 zeros to the end to get 500. Let's say I did 5 times 10,000. I'd do 5 times 1, that's 5, and I'd attach 1, 2, 3, 4 zeros to the end. 1, 2, 3, 4 zeros, and I'd get 50,000. Okay? So it's a simple multiplication fact, but once we learn it and understand how to use it, it can greatly speed up our multiplication. You'll come across a lot of problems with trailing zeros, and you might not have a calculator to use. So this is a trick that can speed you up significantly. So just to look at the official procedure, essentially you just want to leave off any trailing zeros and multiply the numbers that result. And then next you want to attach the total number of trailing zeros, and this is between all factors, to the right of your product. So again, super easy to do. Let's just look at some examples. All right, so let's start out with 3 times 60. So we want to multiply and leave off the trailing 0 in this case. What would 3 times 6 be? That's 18. And then all we need to do is attach the total number of trailing zeros between all factors, in this case just 1, to the end of that number. So we end up with 180, and of course that's correct. 3 times 60 is 180. What about 17 times 1,000? Well, we'd multiply 17 times 1, right? You would leave this part off. These are the trailing zeros. 17 times 1 is 17. And then you would just attach them to the end of the number. I have 1, 2, 3 trailing zeros. So I write 1, 2, 3 zeros there. And so 17 times 1,000 is 17,000. All right, let's look at an example where both numbers have trailing zeros. Here we have 70 times 300. So 70 has 1 trailing zero. 300 has 2 trailing zeros. And essentially just leave those off. Leave those off. And you would do 7 times 3. 7 times 3 is 21. And then I'm going to attach 1, 2, 3 zeros to the end, because that's how many trailing zeros there are between all the factors. So 1, 2, 3 trailing zeros are attached. And so 70 times 300 is 21,000. Okay, what about 153 times 9,000? So a lot of us cannot do 153 times 9 in our head. I'm going to do 153 times 9 in vertical multiplication format. And then when I'm done, I'm going to take this result, bring it up here, and attach 3 zeros to it. All right, so 9 times 3 is 27. Put a 7 down, carry the 2. 9 times 5 is 45. Plus 2 is 47. Put a 7 down, carry the 4. 9 times 1 is 9. Plus 4 is 13. So I get 1,377. So 1,377. And I'm just going to attach 3 zeros to the end of that. 1, 2, 3, comma, comma. And so our result is 1,377,000. Okay, let's look at another one. We have 216,000 times 108,000. So we have 3 trailing zeros here, and we have 3 trailing zeros here. So I'm just going to multiply 216 times 108. 216 times 108. And when I'm done, I'm going to attach 1, 2, 3, 4, 5, 6 zeros to the end of whatever the result is from that. So 8 times 6 is 48. Put an 8 down, carry a 4. 8 times 1 is 8, plus 4 is 12. Put a 2 down, carry a 1. 8 times 2 is 16, plus 1 is 17. 0 times 216 is 0. So I can put a 0 here, or I can leave it off. Doesn't really matter. I'm just going to leave it off. And next we move to this 1 here. I have 1 times 216. Remember, the 1 is in the hundreds place, so I have to start my answer in the hundreds place. And 1 times anything is just itself. So 1 times 6 is 6, 1 times 1 is 1, and then 1 times 2 is 2. So we find our sum, bring down the 8, bring down the 2, 7 plus 6 is 13, put a 3 down and carry the 1, 1 plus 1 is 2, 2 plus 1 is 3, and then bring down this 2, and we get 23,328. Now, I'm going to bring this guy up here, 23,328. And I'm going to attach 6 zeros to it. So let me actually write it a little bit lower. 23,328. 1, 2, 3, 4, 5, 6. So this is our answer for 216,000 times 108,000. We get the result of 23,328,000,000. For the final problem, we have 5,300,000 times 1,615,000. So I just need to do 53 times 1,615. Right? These trailing zeros I'm going to cut off, and I'm going to cut these off as well. We have a total of 1, 2, 3, 4, 5, 6, 7, 8 between the factors. So 8 zeros. So I want to do 1,615 times 53. 3 times 5 is 15. Put a 5 down, carry the 1. 3 times 1 is 3, plus 1 is 4. 3 times 6 is 18. Put an 8 down, carry the 1. 3 times 1 is 3, plus 1 is 4. Okay, now we're moving left to the 5. Remember, the 5 is in the tens place, so we start our answer here. 5 times 5 is 25. Put a 5 down, carry the 2. 5 times 1 is 5, plus 2 is 7. 5 times 6 is 30. Put a 0 down, carry the 3. 5 times 1 is 5, plus 3 is 8. And now we add. Bring down the 5. 4 plus 5 is 9. 8 plus 7 is 15. Put a 5 down, carry the 1. 1 plus 4 is 5. Bring down the 8. We get 85,595. So now we're going to take this result here, 85,595, and we're going to attach to the end of that 8 trailing zeros, right? Because that's what we had between the factors. So 1, 2, 3, 4, 5, 6, 7, 8, comma, 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 comma. So we end up with 8,559,500,000,000 as the answer. Hello and welcome to Pre-Algebra Lesson 13. And in this video, we're going to talk about the properties of division. Okay, so for our lesson objectives, we want to learn how to identify the parts of a division problem. We want to learn the properties of division. And also we want to learn how to solve division problems with remainders. Okay, so let's begin our lesson by thinking a little bit about what happens when we divide one whole number by another. And I'm going to start by just taking a look at 6 divided by 3. And you'll see I have an illustration that I drew. And it's a very simple illustration, but it'll get the point across. Basically, I have 6 boxes here. Let's label them 1, 2, 3, 4, 5, and then 6. And if you look at the division problem, 6 divided by 3, this amount on the left, 6, is what we start with. We have this 6, and that's what I have in the illustration. I have 6 items, 6 boxes, however you want to think about it. Then we're dividing by 3, okay? What does it mean when you say the word divide? It means you're cutting something up or you're splitting it up. So to divide by 3 means I'm going to ask the question, how many equal groups of 3 can I make out of this number 6? That's all 6 divided by 3 is saying. If I just look at the illustration, it's very easy to see that I'd have 1, 2, 3. So this would be one group. And then you could say 4, 5, 6. We know that's 3. I could erase this and make it more clear by saying, okay, this is another group of 1, 2, and then 3. So we would end up with 2 equal groups of 3 that can be made out of the number 6. So then 6 divided by 3 is equal to 2. Now, another way you can think about this is by using subtraction. So I could take and count how many times we can subtract 3 away from 6 until the result is 0. Okay? So if I started with 6 and I said, okay, I'm going to subtract away 3, what's the result? Well, it's going to be 3. Okay, so now I'm going to take 3 and subtract away another group of 3, and now the result is 0. So I was able to do this twice. So again, that tells me that 6 divided by 3 is 2. Now, I want you to look at how closely division and multiplication are related to each other. Forget about the fact that we have a problem 6 divided by 3. So let's just look at this and think back to multiplication. When we saw this, we had 1, 2 groups of 3. So what is that? That's basically 3 plus 3, or 2 times 3. And we know this equals 6. Well, if I kind of look at 2 times 3 equals 6, and 6 divided by 3 equals 2, I kind of see a little pattern that's going on here. And I'm going to show you that pattern real quick. So if I have 6 divided by 3 equals 2, then that means that this number right here, the result, which we're going to learn later on is called the quotient, times this right here, the 3, which we're going to learn later on is called the divisor, should give me this back, this 6, which we're going to learn later on is called the dividend. So if 6 divided by 3 equals 2, then that means that 2 times 3 equals 6. You can kind of think about this as going backwards. Right? I take this number and I go this way. So we'd have 2 times 3 now, and that should equal 6. And you can use this to solve a lot of basic division problems. If I have something like, I don't know, let's say 15 divided by 3. What does that equal? Or how would I figure that out? Well, I could say, well, what number times 3 equals 15? Right? What number times 3 equals 15? Well, we know our times tables pretty well at this point. We know that 5 times 3 equals 15. So the answer to 15 divided by 3 would be 5. And you can check this by using the subtraction method that I just did, or you could draw out 15 boxes and you could split them up into equal groups of 3. You're going to see either way that you get 5 as a result. Okay, let's take a look at another one. So here we have 8 divided by 2. And I'm just going to do the same thing basically. I have made another illustration here, and we have 1, 2, 3, 4, 5, 6, 7, 8. What are we asking for when we say 8 divided by 2? Again, it's how many equal groups of 2 can be made from the number 8. Well, and I'm just going to go ahead and relabel this. And I know I keep doing that, but I'm just trying to make things clear. So here's 1, 2. That's one group. Here's 1, 2. That's another group. Here's 1, 2. That's a third group. Here's 1, 2. That's a fourth and final group. So we have one group of 2, second group of 2, third group of 2, and a fourth and final group of 2. So that tells me that 8 divided by 2 is equal to 4. And again, if I want to use subtraction, I can do it that way as well. So I can say, okay, how many times can I subtract 2 away from 8 before the result is 0? So 8 minus 2 would give me 6. Then 6 minus 2 would give me 4. Then 4 minus 2 would give me 2. And then 2 minus 2 would give me 0. So you can see I did 1, 2, 3, 4 operations to get that. So the answer would be 4. And then lastly, probably the method you're going to use most often until you have everything memorized, you would say, okay, 8 divided by 2 equals what? Okay, equals what? Well, remember, I can go backwards. I can say, what times 2 equals 8, right? Go backwards. What times 2 equals 8? Again, we know our times tables by heart at this point, so we know that this answer would be 4, right? We know this answer would be 4. 4 times 2 gives us 8. Okay, so now that we've talked a little bit about the basics for dividing whole numbers, let's talk a little bit about some terminology. So there are 3 parts to a division problem. The first part, the leftmost number, the number that we're going to split up or cut up, is called the dividend. Okay? Again, that's the left number. This is the number that is being divided or split into equal groups. So when we looked at 6 divided by 3 equals 2, 6 was the dividend. Okay, 6 was the dividend. Okay, the next part of a division problem is called the divisor. And this is the number we are dividing by. So where 6 divided by 3 equals 2, this 3 is the divisor. This is the divisor. And then lastly, you have a quotient. So this is the result of the division operation. So in this case, it would be 2, right? Because 6 divided by 3 gives us a result of 2. So that is the quotient. Okay, so let's do a real quick exercise. We want to label the parts of each division problem. So we have 10 divided by 5 equals 2. So 10, the number on the left, the number or the amount that we start with, is called the dividend. This is the dividend. 5, the amount that we're dividing by, is called the divisor. And then 2, the result of the division operation, again, is called the quotient. This is the quotient. Okay, here we have 20 divided by 10 equals 2. Again, this number on the left, this 20, the amount we start with, is the dividend. Then we're dividing by 10. So that's your divisor. And then lastly, the result from this division is 2. So that is your quotient. Okay, let's talk about a few important properties of division. The first thing is that division is not commutative, meaning the order is important when you divide. And we've seen this before with subtraction. We saw that when we subtracted, when we did 6 minus 3, it was not equal to 3 minus 6, right? Those did not produce the same result. So with division, if I do 6 divided by 3, I will not get the same result if I flip this and put 3 divided by 6. The order does matter when you divide. Okay, the next fact is that 0 divided by any non-zero number is always 0. We're going to cover why I said non-zero in a second. But if I have 0 divided by whatever it is, as long as it's not 0, I'm going to get 0 as a result. So let's say it's 17. And think about why that's the case. Remember, if I go this way and make a related multiplication statement, 0 times 17 equals what? It equals 0, because 0 times any number is always 0. Okay, so this is a very important rule that you need to remember. We can never divide by 0, ever. When we see a problem and 0 is the divisor, we write the answer as undefined. Undefined. So, for example, if I were to write a problem like 6 divided by 0, you don't try to solve that. You just say it's undefined. Undefined. That's all you need to put next to it. And you might think a little bit about why this is the case, and I don't want to get into algebra or anything like that, but just think about the fact that if you have 6 divided by 0, it equals what? Just try to come up with a solution there. Well, do the related multiplication. So something times 0 equals 6. Well, you come across a bit of a conundrum there because we know that when we multiply by 0, we get 0. So what number can you think of that when you multiply by 0 produces 6? You can't find any. So this is why we just say that it's undefined. We just stop because we end up with sort of nonsensical statements like this. All right, the next thing is when we divide a number by itself, the result is 1. And I put except 0. Okay, you can't divide 0 by itself because you can't divide by 0. So if I have something like, I don't know, let's do an easy one. Let's say 4 divided by 4, this is 1. And think about why that's the case. How many equal groups of 4 can I make out of 4? Well, only 1, right? If I were to draw 1, 2, 3, 4 boxes, well, I can only make one group of 4. And it's the same no matter what you do. If I was to say 132 divided by 132, I'd still get 1. Because if I drew out 132 boxes, and I said, well, how many equal groups of 132 can I get out of that? Well, just 1. Right? So that works for any number as long as it's not 0. Okay, so another important rule. When we divide a number by 1, okay, by 1, the result is itself. So, for example, let's say you have 5 divided by 1, you get 5. Okay, 5 divided by 1, you get 5. And think about that in terms of the related multiplication statement. If you think about the 5 there, just say question mark, what times 1 equals 5? Okay, what times 1 equals 5? Well, we know the answer to that is 5. And another way to think about it is, again, using your groups. So if I have 5 of something, let's say they're boxes, and I split it up into equal groups of 1, well, I'm always going to get that number back. So 1, 2, 3, 4, 5, right? And that works with any number. And you can even use that one with 0 because you can divide 0 by a number. I could divide 0 by 1. There's no problem there. 0 divided by 1 just equals 0. I just can't divide by 0. Okay, now let's talk a little bit about division problems where you have a remainder. So this basically means that you're going to have some amount left over. And the way we talk about remainders when we're in grammar school is different from how we're going to talk about it when we kind of move forward in math and we're using, calculators and we've learned how to work with fractions and decimals and so on and so forth. So what is 7 divided by 3? Well, I have an illustration here with 7 boxes. And think about splitting up the 7 boxes into equal groups of 3. What do you get? Well, I can see clearly this is 1, 2, 3 here. Here's 1, 2, 3. So those are 2 groups. But I have this 1 over here, and I have nothing else to kind of pair with it to make another group. So that's a leftover amount. I can't do anything with it. That's considered a remainder. So the answer for 7 divided by 3 would be 2 with a remainder of 1. Okay? 2 with a remainder of 1. And when we check our division and you have a remainder, you have to do it a little bit differently. So now I'm going to multiply this part right here, which is still called the quotient. Okay? Still called their quotient. But then when I'm done, so I'll do 2 times 3, 2 times 3. And once I'm done with that operation, I add my remainder to get back to the original number, the dividend. Okay? So 2 times 3 plus 1 would give me 7. So a little bit different to check when you have a remainder involved. So another way, again, to think about this would be to use subtraction. And if we wanted to subtract, we would do 7 minus 3. This would kind of be the first time. That would give us 4. Then the second time we would do 4 minus 3, and that would leave us at 1. Now I can't subtract another 3 away. In other words, if I do 1 minus 3, I'm going to end up with a negative value, which I know we haven't talked about yet, but basically I'm going to pass 0. So I don't want to do that. I wanted to stop when I got to 0. So we're going to have to stop here at 1. So that's my remainder. That's my remainder. Okay, so before I move on, I want to talk a little bit real quick about the difference you might see when you do this on a calculator. So all of us have done division on a calculator. So you punch in 7 divided by 3, and you get something that says something like 2.3333. And basically this 3 is going to repeat forever. So I'm just going to stop right there. I'm going to put 1, 2, 3 dots. This repeats forever. When we did our division, we said that the answer was 2 with a remainder of 1. So what gives? Why is there a discrepancy in the answer? Well, we haven't gotten to fractions yet. We haven't gotten to decimals yet. But essentially, your calculator is taking this 1, the remainder, and it's dividing it by 3. And this part right here that comes after that decimal point is the result. And again, we're going to cover that later. So for right now, until we feel comfortable with that, until we've covered that, we're going to write this as 7 divided by 3 is equal to 2 with a remainder of 1. Okay, let's look at another example. And again, we're going to have a remainder here. So we have 19 divided by 8. So how would we figure that out? Well, again, we could use subtraction. We could count out how many times we can subtract away 8 from 19 until we get to 0. So let's do it that way. So kind of the first time, 19 minus 8 would give us 11. And then the second time, 11 minus 8 would give us 3. And kind of when we go to do a third time, we have 3 minus 8. And you think about this as we're going to pass 0 in the wrong direction. I don't have enough to subtract away 8. So we're not going to be able to make a third group of 8 with the number 19. So we've made 2 full groups, and then we're going to have 3 left over. Okay? 2 full groups, so the answer is 2 with 3 left over. And does that make sense? Just think about what that means. 2 groups of 8, 2 groups of 8, 2 times 8, that's 16. Then plus 3 left over, plus 3 left over. That's 19. That's what we started with. So 19 split up into equal groups of 8 would give me 2 equal groups of 8 with 3 kind of left over that I can't make into another group. Now, if you didn't do this with subtraction, if you wanted to start this out kind of with multiplication, you would start out by just kind of guessing. And I know you kind of think about that. What do you mean you were guessing? Well, we'd have to say, well, what number times 8 would give us 19? And you kind of go through your times tables and say, well, I don't know of any whole numbers that multiply with 8 and give us 19. So you try to get as close as you could. You'd say, okay, well, 1 times 8 equals 8. 2 times 8 gives me 16. 3 times 8 gives me 24. And when you get to this point, this number's too big. So you'd stop. You'd say, okay, it's not that number. So we'd use 2 because it's as close as we can get. So if we think about 2 times 8 gives me 16. 2 times 8, again, gives us 16. To get to 19, I need 3 more. So that means I have a remainder of 3. And I know a lot of this, when you first start hearing it, if you've never heard it before, can seem a little bit complex, but really it's not. Let's look at another one, make it a little bit more clear. Okay, so we have 21 divided by 4. So if we have 21 divided by 4, again, we can use the subtraction method. So kind of the first time we do this, 21 minus 4 is equal to 17. The second time we do this, 17 minus 4 is equal to 13. The third time we do this, 13 minus 4 is equal to 9. The fourth time we do this, 9 minus 4 is equal to 5. And the fifth time we do this, 5 minus 4 is equal to 1. Now, when I go to try to make a sixth group, and I would do 1 minus 4, I can't pull 4 away from 1. Not without going into a negative value, which, again, we haven't covered yet. So I have to stop here. I can only make 5 equal groups of 4 with the number 21. And then I have 1 left over. Okay? So the answer here is going to be 5 with a remainder of 1. And again, just thinking about if that's logical to you, if I take the number 5, okay, 5 and multiply it by 4, I'm saying that I had 5 equal groups of 4. So that gives me 20. Okay? And then my remainder was 1. So I add 20 and 1 together to get the original amount, the dividend of 21. And again, if you don't want to use subtraction, you can use multiplication. You can use multiplication. So 21 divided by 4 equals question mark. Again, work backwards. So question mark times 4 equals 21. So do we know a whole number that when we multiply it by 4, we get 21? No. So you can kind of start out and say, well, I know that 4 times 4 is 16. I know that 4 times 5 is 20. And I know that 4 times 6 is 24. Well, 24 is too big. Too big. And we know 4 times 4 is not going to work. That's too small because we could have made another group. So I go with 4 times 5. And once I see my result is 20, all I have to do is say, okay, well, the difference between 21 and 20 is just 1. So that's going to be my remainder. So this would be 5, okay, that right there, with a remainder of 1. Because when I get to 20, I need one more to get to 21. All right, let's look at one final problem. So we have 37 divided by 3. And we're not going to use subtraction here because realistically, you're going to find these answers by using multiplication, right? It's just quicker. So I'm going to put a question mark here. I'm going to put equals question mark. And we're going to work backward using multiplication. So question mark times 3 equals 37. So just thinking about our times tables here, just think about multiplying by 3. What's going to get me close to 37 without going over it? Well, I know 10 times 3 is 30. 11 times 3 is 33. I can keep going. I can keep making more groups of 3. So 12 times 3 is 36. 13 times 3 is 39. Too big. And you could have stopped when you got to 36 because you know multiplying the next number, right, when we got to 13 by 3, would add 3 to 36 and get you to 39. And we just needed to go up by one more to get to 37. So we would stop there and say, okay, well, the result or the quotient's going to be 12. But that's not the full answer because I kind of have one left over, right? I've made 12 equal groups of 3, but I have one left over. So that's my remainder. And again, just to review this, we start with 37, our dividend. We split it up into equal groups of 3, our divisor. We get 12. So we get 12 equal groups of 3. But there's a problem. We have one guy kind of left over, and so that's our remainder. And again, when you want to check something like this and there's a remainder involved, you've got to multiply the quotient times the divisor, and then when you're done, add the remainder. That's going to give you your dividend back. And check this. 12 times 3 is 36. 36 plus 1 is 37. Hello and welcome to Pre-Algebra Lesson 14. And in this video, we're going to learn about long division. The lesson objective for today is to learn how to divide multi-digit numbers using long division. Okay, so far in our pre-algebra course, we have reviewed how to do addition with whole numbers, how to do subtraction with whole numbers, and how to do multiplication with whole numbers. Now, what we saw in each case is that when we had large numbers that we were working with, like let's say with addition, if we wanted to add two large numbers together, we didn't do it in our head. We used a process called vertical addition. And what vertical addition does is it breaks it down into a series of easier steps. So, for example, if I want to add 24,322 and, I don't know, let's say 308, I didn't just go, okay, this is the answer. I would write 24,322 on top, 308 on the bottom, and I would go column by column until I got an answer. So essentially what we're doing again is breaking this down into a series of easier steps. Now we saw the same thing when we were subtracting large whole numbers. We used a vertical subtraction. Also when we were multiplying large whole numbers, we used a vertical multiplication. This is what long division is going to do for us. In the last lesson, we learned how to do some basic division, but we didn't see any division with, large whole numbers. So if I asked you to do something like 20 divided by 4, pretty much everybody can do that without a long division. So 20 divided by 4 is what? You would use a related multiplication statement to find the answer. What times 4 equals 20, right? And from your knowledge of the times tables, you know that question mark would be replaced with a 5. And so 20 divided by 4 is 5. But what if I asked you, what is 2,642,311 divided by 1,622. Most people cannot do that in their head. I definitely cannot. Now, I've met some people in college that could, but the majority of us cannot. So we would use a long division to solve a problem like that. And all long division is going to do is break this problem up into a series of manageable steps. Let's start out by looking at a very simple problem, one that we can do without long division. I'm going to go through the steps here, and we're just going to work a lot of problems. I know most of you have done long division before, and this is going to just be a review. But even if you haven't, you can pick it up from this lesson. So let's try something like 30 divided by 6. That's an easy one. So to set up a long division, you'll have this new symbol, and it looks like this. And there's some variations of this. Sometimes you'll see your teacher go straight down. However you want to do it, I don't think it matters. You're just trying to get a result here. So whatever you're comfortable with. I try to make mine look like that. Now, you take your dividend. Remember, that's the left number of the division problem. That's the amount you start with. This is the dividend. That's going to go underneath the symbol. And a lot of teachers will call this the house. So it goes underneath the house you might hear. So the 30 goes there. This is for the dividend. Now, your divisor, which is 6 in this case, this is your divisor, is going to go to the left of this symbol. So it sits out here. This is for your divisor. Okay? Now, once you've set up the division problem like this, you go through a series of steps. Now, I'm going to write those steps down. I want you to copy them down on your paper. You have to memorize them. And there's a little trick I'm going to give you to do that. So the first step is to divide. And you're not going to divide the whole thing. You're going to basically take the dividend on one digit at a time. Okay, and I'll show you how to do that in a minute. So you divide, then you multiply, you subtract, you bring down, and then kind of this next step is repeat or remainder. And this will kind of make more sense once we get into the problem, but basically what this is telling you is that, again, you have a series of steps to get your answer, so you're going to have to repeat the process sometimes. When you come to the end of that, and there's no more numbers to say bring down, you're going to have a remainder. And in some cases, you're not going to have a remainder. The remainder might be 0. It doesn't matter. This is basically telling you, hey, stop the problem. You have your answer. All right, now how do we remember something like this? I know in a lot of places we'll have kind of tricks to remember stuff. When you get to the order of operations, you're going to hear something like, please excuse my dear Aunt Sally, for parentheses, exponents, multiply, divide, addition, and subtraction. Well, the trick for the long division is going to be dad, mom, sister, brother, rover. Okay? You think about your family. So the D in dad for divide, the M in mom for multiply, the S in sister for subtract, the B in brother for bring down, and then the R in rover for repeat or remainder. So again, that's a little trick you can use to remember the steps. All right, now having said that, let's kind of move into our actual division. So what we're going to do is we're going to start by asking a question. We take the divisor here and we ask how many times does it go into the leftmost digit of the dividend? Okay, we're going to attack that dividend one digit at a time. So how many times will 6 go into 3? Now, a lot of people don't know what this terminology means when I say, how many times will 6 go into 3? All that's asking is, what is 3 divided by 6? What is 3 divided by 6? These two things are the same. If your teacher asks you, how many times will 6 go into 3? And what is 3 divided by 6? She asks you the exact same question. It's just a different way to put it. So 6 goes into 3 0 times. And I want you to think about why. So I'm going to erase this real quick. And I want to think about 3 boxes. 1, 2, and then 3. Remember, if I say, what is 3 divided by 6? I'm taking 3 and I'm splitting it up into equal groups of 6. Now, we are not using fractions or decimals. Some of you are going to go out, oh, that's 0.5 or oh, it's 1/2. Well, if we're only using whole numbers, which is what we're doing here, the answer is 0. And the reason is because I cannot make a group of 6 having only 3 items. If I have $3 in my wallet and I need $6 to purchase a hamburger, I'm not going to get the hamburger, okay? Unless somebody loans me another $3. So the answer would be 0 with a remainder of 3, okay? 0 with a remainder of 3. I made 0 groups and I had 3 left over. Now, with long division, you never think about this part until the very end. So I'm never going to include this in my answer that goes up here. So once I ask how many times will 6 go into 3, I take this quotient part, and just this part, not the remainder, and I put it directly over what I was working with, okay? You have to think about place value when you're working with the long division problem because you're lining this up with the 3. That's what I was working with. I've done my first step here, which was to divide. Now I'm going to multiply. And what I multiply is the answer that I just had times the divisor. So 0 times 6. We know that 0 times any number is always 0. So 0 times 6 is 0. So that step is done, and then we subtract. Now, notice that I wrote the 0 directly underneath what I was working with. We're always going to do that. Line everything up by place value with what you're working with. So I'm going to subtract here. 3 minus 0. That's going to give me 3. And then I'm going to bring down. We're always going to be bringing down the next digit to the right. Next digit to the right. So now this is going to be a 30. And now we have this step that says repeat or remainder. So I just brought down this 0 to make a new number 30. So I'm going to repeat this process and go back up. And I'm going to start by dividing again. So now I'm going to ask how many times will 6 go into 30. So I'm basically saying, what is 30 divided by 6? Okay, remember that's the same thing. If I say how many times will 6 go into 30, or what is 30 divided by 6, I've asked you the same question. So 30 divided by 6 equals what? We can solve this using our times tables. Remember, you just work backwards. What times 6 equals 30? Well, 5 does. So the answer would be 5. Now, I write 5 directly to the right of my previous answer. Remember, I was working with this 30 here. Where's the ones place for the 30? It's right here, so I'm going to line up that 5 right there. Now I go through my steps again. I'm going to multiply. Okay, I'm going to multiply. So 5, which is the answer we just got, times 6, the divisor, gives me 30. Write it underneath what you had. That's what we're working with. We got to line everything up based on that. Then we're going to subtract. 30 minus 30 is 0. And then we want to bring down. But there's nothing else over here to bring down. If I highlight this section over here, you see no more numbers to the right. So we're done bringing stuff down. So when we get to this step where it says repeat or remainder, if I had nothing else to bring down, I don't repeat. I go to the remainder part. Now, because this is 0, I know we say remainder there, but because this is 0, there basically is no remainder, right? So we think about 30 divided by 6, it's 5 with no remainder. So to think about this more clearly, if I had 30 boxes and I split it up into equal groups of 6, I would end up with exactly 5 of those groups, right? I wouldn't have anything left over. Now, I know that for some of you, you'll be like, well, what step goes where? As you work more problems, you will get this down. You memorize this just like you memorize anything else. Over time, this will not be complicated at all. Now, I want to show you a little trick that you're going to use. And some of you will already be screaming and saying, why did you put a 0 right here? My teacher doesn't show me that. Well, the other way is kind of a shortcut. So let me erase this real quick. And I'm going to show you some other way. Recall that if I have a 0 next to this 5, this is still 5. Right? 5 is the same as a 0 and then a 5. Or if I put 0, 0, 0, 5, that's the same as 5. These zeros to the left of 5, they don't add any value to the number whatsoever. Now, let me start this problem over and show you what we could have done. So for the first step, divide, we could ask, okay, how many times does 6 go into 3? If you know you're going to get a result of 0, what you can do is just expand your selection to include the next digit to the right. Okay? So now I can just ask, how many times does 6 go into 30? Realize that if I would have done this the first way, how many times does 6 go into 3? 0. 0 times 6 is 0. Subtract and I get 3. bring down the 0, I'm expanding my selection here anyway. I'm doing the exact same thing. It's just taking me longer because I went through all these steps to do it. So the shortcut is just start out by saying, okay, how many times does 6 go into 3? 0 times. Okay, so I can just expand this and say, now how many times does 6 go into 30? We know the answer is 5 already. And the main thing is maintain your place value by putting the 5 directly over that 0. Think about that number 30. Where's the ones place for 30? Well, it's where the 0 is, so I'm putting the 5 there. And alternatively, if that's hard for you to remember, each time you kind of expand your selection, you would have had a 0. So I passed up that 3, so I would have had a 0 there. Right? Just think about it that way. Either way you do it, you're going to end up with 5. So then you would multiply 5 times 6 is 30. We'd subtract and get 0. Nothing to bring down over here. And so where it says repeat, we don't do that. We didn't bring anything down. Our remainder would be 0, meaning we don't have a remainder. And so 30 divided by 6 is 5. Okay, let's look at a slightly more challenging problem, but one that's still easy. Okay, I want to take a look at 100 divided by 5. So 100 divided by 5. What is that going to be? Again, we're going to set this up in long division format. So we're going to have this symbol that we're going to use. Remember, your dividend, which is 100, is going to go underneath, and the 5 is going to go off to the left. That's your divisor. Now, what are our steps? Let me try to paste this, and I'll put that right there. So here's our steps. Remember, you can think about your trick. Dad, mom, sister, brother, and then Rover. Now, we're going to start with divide. So take your divisor, and then take on your dividend one digit at a time. So 5 goes into 1. How many times? So basically I'm asking, what is 1 divided by 5? That would be 0 with a remainder of 1. Right? If I had one box and I said split it up into equal groups of 5 using whole numbers, again, not using fractions or decimals, I'm not going to be able to do that. Right? I can't even make one group because I only have 1. I need 4 more to make just one group. So the answer would be 0. And again, we don't think about the remainder until the end. So I can put a 0 here, or I can use my shortcut. Remember, if I put 0 here and I go through and I multiply, 0 times 5 is 0. I subtract, I get 1. I bring down, I have 10, and then I would repeat. I could have gotten this 10 here just by expanding and not putting a 0 there. Right? So this is the shortcut. So I can say, how many times will 5 go into 10? 5 will go into 10 twice. Right? If you think about what is 10 divided by 5, go backwards. What times 5 equals 10? We all know from the times tables that that is 2. Now the main thing again is to maintain the place value. I don't want to put a 2 right here. If I think about that relative to this number 100, I'm saying that that 2 is in the hundreds place and it's not. Okay? That 2 needs to be relative to this 0. Think about it in terms of this. I was working with the number 10. Where's the ones place for the number 10? It's where the 0 is. Okay? It's right there. So I want to put the 2 directly in line with the ones place from 10. And again, alternatively, think about the fact that we would have had a 0 here if we would have done it the slow way. So 0, then 2. Okay, now we multiply. 2 times 5 is 10. And again, you want to line that up with the 10 and then subtract. 10 minus 10 is 0. Then bring down, so it's always the next digit to the right. And then repeat or remainder. Now, 0, 0 is the same thing as 0. Okay, I don't need 2 zeros there. I can just use 1. So when we repeat, we just go back up to the top and we divide. What is 5 into 0? Again, think about this using the properties of division. So I'm basically asking 0 divided by 5 equals what? Remember, if you take 0 and you divide it by a non-zero number, the answer is always 0. Okay? And if you reverse that, you can see why. What times 5 equals 0? Well, when you multiply, 0 times anything is always 0, so the answer is 0. Okay, so I write my 0 directly to the right of that 2, and then I'm going to multiply. 0 times 5 is 0, subtract, get 0, and then there's nothing else over here to bring down. So when we get to this step where it says repeat, we don't repeat because there's nothing else to repeat with. We have our remainder or our termination step. Now, this remainder is 0, meaning we don't have a remainder. So 100 divided by 5 is 20, no remainder, meaning if I had 100 of something, let's say boxes, I split them into equal groups of 5, I would get exactly 20. All right, let's take a look at another one. So we have 315 divided by 9. So again, we're just going to set up our long division. 315 divided by 9. Again, your dividend goes underneath. Your divisor goes to the left. Okay, so again, we want to divide, multiply, subtract, bring down, then repeat or remainder. Dad, mom, sister, brother, and then rover. Okay, so we start with divide. So we have our divisor here. And again, we're going to take on the leftmost digit of that dividend. So how many times will 9 go into 3? Meaning, what is 3 divided by 9? Well, you can't do 3 divided by 9 with whole numbers, right? 3 divided by 9 would just be 0, remainder 3. So we can just expand our selection and say, okay, well, it's not going to go into 3. How many times would it go into 31? How many times would it go into 31? So 31 divided by 9 equals what? Again, work backwards. What times 9 equals 31? Well, using our times tables, we know that there's no number or whole number that multiplies with 9 to give you exactly 31. So we have a situation where we want to get as close to 31 as possible without going over. So if I think about 3 times 9, that's 27. 3 times 9 equals 27. 4 times 9 would give me 36. This is too big. 36 is bigger than 31, so I have to go with 3. That's as close as I can get. So let's erase this and we'll put 3 down as our answer. And again, make sure to line that up with the ones place of 31, which we were just working with. So the 3 is going to go here. And again, alternatively, I would have had a 0 here if I'd have went through the long way, right? When I said 9 goes into 3 0 times. So that's where your 3 is going to go. Now, we need to multiply, and let me kind of fix this a little bit. We need to multiply. We're going to do 3 times 9, okay? That's going to give me 27, and write that underneath the 31, right? Just underneath what we were working with. Then we're going to subtract. So I'm going to borrow here, and then 11 minus 7 is 4. 2 minus 2 is 0, so I just leave that blank. I don't need to put that. And then I bring down. Always the next number to the right. And I'm going to repeat, right? I brought something down. I have something new to work with. And I'm going to divide again. So 9 goes into 45. How many times? 45 divided by 9 equals what? Well, this one's simple. We can use our knowledge of the times tables to do this. What times 9 equals 45? Most of you will know that 5 times 9 is 45. So the answer would be 5. So I put a 5 directly next to that 3. So now we'd multiply. 5 times 9 is 45. And then subtract. We will get 0. Nothing else to bring down over here. I don't have any more digits to the right. So when we get to this step, we're not going to repeat. We just say, hey, we're at our step where we have our remainder. Now, the remainder is 0, meaning we just don't have one. It just tells us to stop, right? We've got our answer. So 315 divided by 9 is 35. And let's go ahead and check this. And particularly when you start out, you want to check everything. Just make sure you get the right result. And if you didn't, go back and see what you did wrong. It's probably some silly mistake. As long as you understand how to do the steps and you get the wrong answer, go back and check it and make sure that you didn't just make a silly mistake. The answer here is 35. And working backwards, 35 times 9 should give us 315. 9 times 5 is 45. 9 times 3 is 27, plus 4 is 31. So yes, we do in fact get our dividend back. So we have the correct answer. Okay, let's take a look at 942 divided by 3. So 942 divided by 3. And let's paste our steps. Okay, so again, we have divide, multiply, subtract, bring down, and then repeat or remainder. So we start out by asking how many times will 3, the divisor, go into the leftmost digit of that dividend. So in this case, it's 9. Now, 9 is bigger than 3, so we're not going to get a result of 0 here. We're basically saying, what is 9 divided by 3? I think all of us know that off the top of our head. It's 3, right? But if you didn't, you could just say, okay, well, what times 3 gives me 9? From your knowledge of the times tables, you know that would be 3. So put your answer directly above what you're working with. I'm working with that 9, so I'm going to put that 3 right there. And then I'm going to multiply. 3 times 3 is 9. Write that directly underneath the 9, and then subtract. 9 minus 9 is 0. And then we bring down. So I'm going to bring down this 4 here. So now we repeat the process, and we want to divide again. So how many times will 3 go into 4? Well, just once, right? If we think about what is 4 divided by 3, I would get 1 with a remainder of 1. And again, we don't think about the remainder until the very end, so we just put this part. So the answer would be 1. And notice how I write it directly to the right of that 3, okay, maintaining place value. Now I multiply. 1 times 3 is 3. Then I subtract. 4 minus 3 is 1. Then I bring down. So I'm bringing down the next digit to the right, which is a 2. And then I repeat. Go back up, and we're going to divide again. And again, as you do this more and more, you see that these steps become very, very easy to go through. It just becomes very mechanical for you, right? Divide, multiply, subtract, bring down, repeat. Divide, multiply, subtract, bring down, repeat. And then at some point, you run out of numbers to bring down, and you end up with a remainder, which in some cases will be 0, meaning you don't have a remainder. Okay, so we divide again. 3 goes into 12. How many times? I'm asking, what is 12 divided by 3? And again, I can use a related multiplication statement and just ask, okay, what times 3 would equal 12? And from our knowledge of the times tables, we know that that would be 4. So I'm going to write a 4 directly next to that 1. And now I'm going to multiply. 4 times 3 is 12. Then we subtract. 12 minus 12 is 0. Nothing else to bring down. And so we're not going to use this repeat step. We go to the remainder, right? And the remainder is 0 here, meaning we don't have one. So 942 divided by 3 is exactly 314. And let's check it. Just going to work backwards and say, okay, well, 314 times 3 should be 942. 3 times 4 is 12. 3 times 1 is 3, plus 1 is 4. 3 times 3 is 9. 942. Again, that's our dividend that we started with. All right, let's take a look at one that will have a remainder. So 461 divided by 2. And again, our steps for the division: divide, multiply, subtract, bring down, and then repeat or remainder. All right, so we're going to start with divide. How many times will 2 go into 4, the leftmost digit of this dividend? Well, 4 divided by 2 is 2. I think all of us know that by now. So I'm going to put a 2 right here directly over that 4 that I was working with. And let me move this down just a little bit. And now I can multiply. 2 times 2 is 4. And put that directly underneath the 4 that you're working with and subtract. 4 minus 4 is 0. Now we bring down the 6, the next digit to the right, and we repeat, right? We go back up when we divide. So 2 goes into 6 how many times? Well, 3 times, right? Because 6 divided by 2 is 3, right? 3 times 2 is 6, so 6 divided by 2 is 3. So now we multiply. 3 times 2 is 6. Subtract. 6 minus 6 is 0. Bring down. I'm bringing down a 1 here. And then I'm going to repeat. I want to divide again. How many times will 2 go into 1? Well, it's not. If your divisor is smaller than your dividend that you're working with here, then you're not going to be able to do it using whole numbers. You're going to end up with a fraction, which we're going to cover later on. But for right now, 2 is not going to go into 1, right? You get a result of 0, remainder 1, which we don't think about the remainder till the end. So 2 goes into 1 0 times. Then you multiply. 0 times 2 is 0. And then we subtract. So let me kind of scroll down. 1 minus 0 will be 1. And nothing else to bring down over here. So we end up with repeat or remainder. We're not going to repeat. We didn't bring anything down. We actually have a remainder that's not 0 now. So the remainder is 1. And for most teachers, they want you to drag this back up here and write it next to the quotient. So I would write R1 like that. So 230 with a remainder of 1. Now I want you to remember what you do to check something with a remainder. It's a little bit more tedious. So you will multiply the quotient, which is 230, times the divisor to start. So 230 times 2. A lot of you can do that in your head because of the trailing 0 trick, right? 2 times 23 is 46. Put a 0 at the end, you get 460. But the long way, 2 times 0 is 0, 2 times 3 is 6, 2 times 2 is 4. Now, when I'm done with that, I would add to that the remainder, the amount that was left over. So 460 plus 1 would be 461. And think again why this is the case. I started out with 461 boxes. I split them into equal groups of 2. I was able to make 230 of those groups, but then I had 1 left over, right? I only used 460 out of the 461. I've got 1 that's just hanging out by itself. It doesn't have another box to make into another group of 2. So that is my remainder. Okay, let's take a look at another one. We have 193 divided by 9. So 193 divided by 9. And again, where's the steps? So we start out with divide. 9 goes into the leftmost digit of that dividend, 1 how many times? If this is smaller than this, the result's going to be 0. Okay? So I could put a 0 there, or again, I can just expand the selection and say, how many times will 9 go into 19? Well, 19 is bigger than 9, so I know that that's going to go in at least once. So 19 divided by 9 equals what? What times 9 equals 19? Well, there's no whole number that multiplies with 9 that gives you 19, but 2 times 9 would give you 18. That's as close as you can get without going over. So I'm going to put a 2 as my answer. And again, line that guy up. If I'm working with 19, where's the ones place for 19? It's right here. So that's where my 2 is going to go. Alternatively, as I keep saying, and I know you'll get tired of this, but I want to make sure that you're clear on the place value part, this would have been a 0. So the 2 would just go to the right of that. However you can remember that, place value is important in long division. Now we're going to multiply. 2 times 9 is 18. Put that underneath the 19 and subtract. 19 minus 18 is 1. Now we bring down a 3 there. And then we repeat, right? We go back up to the divide. So how many times will 9 go into 13? Just once, right? Because we found that 9 times 2 was 18. That's too big, so it has to only go in just once. Now we multiply. 1 times 9 is 9. And we subtract. 13 minus 9 is 4. And nothing else to bring down over here, so we're not going to repeat. This is our remainder. Okay, 4 is our remainder. So drag it back up to the top and just put R4, right? Remainder 4. And again, to check something like this, just go backwards. So if this is 21 remainder 4, take your quotient, multiply by your divisor. 21 times 9. 9 times 1 is 9. 9 times 2 is 18. And then add your remainder back in. So 189 plus 4. 9 plus 4 is 13. 1 plus 8 is 9. Bring down the 1. You do, in fact, get 193 back, right? Your dividend. Okay, let's take a look at one with a 2-digit divisor now. So I have 126,323 divided by 15. So nothing is going to change here. The process is the same. When you start getting into bigger divisors, your guesswork becomes a little harder. And I'll show you what I mean by that. So here's our steps here. And we have 126,323. Okay, so we start out by asking, how many times will the divisor go into the leftmost digit of the dividend, right? The divide step. Well, it's not going to go in there. Again, if the divisor, which in this case is 15, is bigger than what you're trying to go into, right? Kind of think about it as your temporary dividend or your step-by-step dividend. In this case, it's 1. It's not going to work, right? You don't have enough to make a group of 15 with 1 using whole numbers again. So you would expand your selection, or you could put 0, whatever you want to do, and ask how many times will 15 go into 12? Well, again, 12 is smaller than 15, so it's not going to work. So again, you can put 0, or you can expand and say, well, how many times will 15 go into 126? Well, I know that I'll go in there, but I just don't know how many times, right? We don't work with 15 and 126 very often. So 126 divided by 15 equals what? So what times 15 equals 126? Here's where we can kind of do some estimating, okay? Now, I can think about 126 as just 120. Make it a little easier for us. And a lot of times you'll be able to get close and see where you need to go, and you can kind of fine-tune it with some extra multiplication. So I know that 10 times 15 is 150 using my trick for trailing zeros. That's too big. So what about 8 times 15? 15 times 8. So 8 times 5 is 40. 8 times 1 is 8, plus 4 is 12. So that's exactly what we need to get to 120. But what we needed was 126. So let's see if that would work out as our answer. So 15 times 8 we know is 120. We need to know what 15 times 9 is. Well, you know how to add and multiply. You know, you would just add 15 to 120. That would give you 135, right? No need to go through and do the multiplication. That's too big. It's larger than 126. So 8's going to be what we're going to use. That's as close as we can get without going over. So we're going to line up that 8 on top of the 6, which is the ones place for that number 126. And then we are going to multiply. So 8 times 15, as I just said, was 120. And then we subtract. 126 minus 120 is 6. Bring down. Always the next digit to the right, so we bring down that 3. And then we're going to repeat. Right? So we go back up and we divide. So how many times will 15 go into 63? So 63 divided by 15 equals what? So what times 15 equals, and let's round this down to 60. Because I think all of us probably know that 4 times 15 would give you 60. And think about it, that's as close as you're going to get to 63 without going over, because 5 times 15 would be 15 more than 60, or 75. So I'm going to use a 4 as my answer. So I'm going to put a 4 here, and then I'm going to multiply. 4 times 15, as I just said, was 60. And then we subtract. 63 minus 60 is 3. Then we bring down. So I'm bringing down this 2 here. And now I'm going to repeat. I want to divide. How many times will 15 go into 32? And this one's kind of easy, because if you just think about doubling 15, what is 15 times 2? It's 30. Right? That's as close to 32 as you're going to get. So we're going to put the answer of 2 and then multiply. 2 times 15 is 30. Then we're going to subtract. 32 minus 30 is 2. And then we're going to bring down. So bring down this 3 here. And now we're going to repeat. How many times will 15 go into 23? Well, we know the answer is 1 there, because 15 times 2, as we just said, was 30. That's bigger than 23, so we have to go with 1. Okay, so now we multiply. 1 times 15 is 15. We're going to subtract. 23 minus 15. We're going to borrow here. 13 minus 5 is 8. And then we're going to bring down, but there's nothing else over here. So we're at our last step. We're not going to repeat. We didn't bring anything down. So we're at the step where we say, okay, what's our remainder? So our remainder is 8. And we could just drag that back up to the top and say, okay, the remainder is 8. Now, I'm not going to go through and check this one because of the amount of work that would be involved. But if you want to check it at home, I advise you to do so just to get the practice. Take this number here, 8,421, multiply it by 15. When you're done, add 8, and you will get this number back, our dividend, 126,323. All right, so let's look at one final problem. We have 163,971 divided by 150. So again, as your divisor gets larger in terms of how many digits it has, your guesswork on each step is going to be harder. So let's write this in long division format. 163,971. Again, we're dividing this by 150. And let me paste the steps here. And so we begin with divide. So how many times will 150 go into the leftmost digit of that dividend? It's not going to go. Right? 150 is bigger than 1, so we expand that to 16. It's bigger than 16, so we expand that to 163. So 150 will go into 163 one time. And again, put the 1 directly over that 3. I can't stress this enough, because I just have a lot of students that'll go, okay, it's once, and they put it over here. In terms of this number here, this, if you think about the whole number, when you have an answer, this looks like it's in the hundred thousands place, but really it needs to be here in the thousands place, right? So it's a completely different answer if you put that 1 over there. So make sure you line that up on top of the 3. And again, alternatively, you pass this number up, so it would have been a 0. You pass this number up, so it would have been a 0 until you got there. So that's where you would have lined it up to. All right, so now we're going to multiply. 1 times 150 is 150. Again, lining that up with 163. And then we're going to subtract. 163 minus 150. 3 minus 0 is 3. 6 minus 5 is 1. Bring down. Okay, we're going to bring down the 9. Can 150 go into 139? No, it cannot. So if I have 139 boxes, and using only whole numbers, I tell you to make a group of 150, you won't be able to. Right? You'd have 0 with a remainder of 139. So we put 0 here. Okay, we put 0 here. And we multiply. 0 times 150 is 0. And some of you at this point might say, okay, well, and over here we just kind of skipped it over. When you have a 0 in the middle of a number, it changes the value of the number. You can't use that shortcut in this case. So if I had 1005, these two zeros do add value to the number. But if I had the number, 17, and I put zeros off to the left, this is not changing the value of the number. So that's why we can skip that there. Once you get going, you can't skip that anymore. So if your result is 0, you have to write it and go through the steps. So 0 times 150 is 0, and then we subtract. So we get 139. Now we bring down. Okay, we're going to bring down that 7. And now we're going to repeat. So 150 goes into 1,397 how many times? So let's do this down here because this is going to be a tough one. So 1,397 divided by 150 equals what? So this is where it gets complicated. We don't know the times tables for 150. So we have to get somewhat creative. Now, using my trick for trailing zeros, 150 times 10 equals 1,500 or 1,500, however you want to think about that number. Now, that's clearly too big, but I can mentally subtract away 150 from 1,500. It's pretty easy to do. It's 1,350. That looks like that's going to work out. So it looks like we need 150 times 9. Right, again, take 150 away from this, you get 1,350. That's as close as you can get to this without going over. We go back up to the top here, and we put an answer of 9, and we multiply. 9 times 150, as I just said, was 1,350. Then we subtract. 7 minus 0 is 7. 9 minus 5 is 4. And then 3 minus 3 is 0, and 1 minus 1 is 0. Again, if you have zeros over here, it wouldn't change the value of the number, so I just don't put them. Right? So we have 47. So now we bring down this 1, and we have 471. So now we want to divide. How many times will 150 go into 471? Well, if I mentally think about 150 times 2, I think everybody can kind of do that in their head. That's going to be 300. 15 times 2 is 30. Put a 0 at the end. So what about times 3? Well, that's going to be 450. Right? I just add 150 to that. Pretty easy to do in your head. So that's as close as we can get without going over, because if I went times 4, it would be 600. Right? Adding it on 150, and that's too big. So we're going to use 3. Okay, we're going to use 3. So I write a 3 here, and then I multiply. 3 times 150 is 450. And I know it's cut off right now, but the next step will be to subtract. Let me scroll back down. 1 minus 0 is 1. 7 minus 5 is 2. And then we want to bring down. But when we come back up here, nothing else to bring down. So we can't repeat. Now we're at our step where we have a remainder. Right? This is what we have left over, and that is 21. So if I drag that back up here, I can just put R21. So again, if you want to check this answer, 1,093 with a remainder of 21, multiply 1,093, which is your quotient, by 150. When you get that result, add 21, and you should get this number back, the dividend, 163,971. Hello, and welcome to Pre-Algebra Lesson 15. And in this video, we're going to learn about exponents. Okay, for the lesson objectives, we want to learn the terminology associated with exponents. We want to learn how to write a repeated multiplication in exponent form. And we want to learn to solve problems that contain exponents. So what exactly is an exponent? Well, let me show you through an example. Let's say we had something like 3 times 3 times 3 times 3 times 3 times 3 times 3. That takes up a lot of room on my sheet. I wish there was an easier way to write that. Well, in fact, there is, using an exponent. Essentially, what I would do to write this in exponent form is I would count the number of 3's that I have there. I have 1, 2, 3, 4, 5, 6, 7. So I would take this number that I'm multiplying by itself, this 3, and I would write it down. So I would have my 3 there. And then I would put an exponent, which is a small little number that goes up in the top right corner, just telling me how many factors of 3 that I have. This number right here is called a base. It's called a base. When you write a number in exponent form, the base is the number that is being multiplied by itself. In this case, it's 3. Right? I have 3 times 3 times 3 times 3 times 3 times 3 times 3. So 3 is the base. The 7, again, this little small number in the top right corner, is the exponent. The exponent. And again, this tells us how many factors of 3 we have. Let's think about another one. Let's say I had 2 times 2 times 2. If I want to write this in exponent form, I have this number 2, that's going to be my base. 2 is going to be my base. Again, it's the number that we're multiplying by itself. And then I'm doing it 3 times. 1, 2, 3. I have 3 factors, so that's the exponent. 3 is the exponent. So for the purposes of pre-algebra, you can just think about an exponent as telling you how many factors of the base you're going to have. Because the only exponents we're going to look at this point will be whole numbers, usually 1 or larger. Okay, and in a lot of cases, it's just going to be 2 or larger. We have some special rules when we start dealing with exponents that are 0 and 1. So essentially for pre-algebra, you're just going to think about it using whole number exponents, and it's going to tell you how many factors of the base that you have. And again, when you think about 0 and 1, you'll have some special rules for those. So any number raised to the power of 1 is just itself. So in other words, if I have 6 and it's raised to the power of 1, and I say, well, what is 6 to the power of 1? Well, it's just itself. It's just 6. Or I could flip that and say, okay, I want to write 12 in exponent form. How would I do that? Well, I would take 12, that would be the base, and then I would take 1 and write that for my exponent. So if you have a number that's just hanging out by itself, let's say 13, and again, you want to write it in exponent form, you just write the number as the base and put a 1 as the exponent. So any number raised to the power of 1 is just itself. Now we have a rule for a number raised to the power of 0, but we're going to cover that later on because that's something we need to go through and explain. So for right now, we're just going to work with, again, whole number exponents that are generally going to be 2 or larger, and we know the rule for 1, so we're safe there. All right, so let's talk a little bit about some language that you're going to hear when you work with exponents. So when we raise something to a power, we generally say the number to the, and then that power. So for example, if I have 14 and my exponent is, let's say, 7, this would be the number, which is 14, and then to the, in this case, it's the 7th power, right? Because it's a 7, so 14 to the 7th power. If I have 8 and my exponent is 4, this would be 8 to the 4th power. If I have 9 and my exponent is 13, it would be 9 to the 13th power, so on and so forth. Okay, so there's 2 special cases that I want you to know. And the first one is when we raise a number to the 2nd power, okay, meaning we have an exponent of 2, we say the number is squared. If you don't know this at this point, take out a pen and a piece of paper and write it down. You need to memorize that because moving forward, you're going to hear that all the time. You're going to have somebody say, what is 6 squared? What is 4 squared? What is 8 squared? And you might be going, I don't know what that means. When we say squared, we're meaning raised to the power of 2. So I could say this as 6 to the power of 2. I could say 6 to the 2nd power, or I could say 6 squared. They all mean the same thing. So very important that you understand that definition. And another scenario that's going to come up, when we raise a number to the 3rd power, we say the number is cubed. So that means you have an exponent of 3. Again, write this down. It's going to come up a lot. So if I have 4 to the 3rd power, we generally will say that's 4 cubed. Now, you're not wrong if you say 4 to the 3rd power, or if you have 4 squared and you say 4 to the 2nd power. It's just you need to know both in case your teacher asks you. They might say, what is 4 cubed? And you go, well, I don't know what that is. You'll be in trouble. So again, memorize that when someone says something is cubed, it means they have raised it to the 3rd power. When something is squared, they have raised it to the 2nd power. Okay, let's do a little basic practice here. We want to write each in exponent form. Nothing that's going to be too complicated. So I have the number 7, and it's being multiplied by itself. So I have 7 times 7 times 7 times 7 times 7. So the base is the number that is being multiplied by itself. So obviously that is 7. Again, this is the base. And then my exponent tells me how many factors of 7 I have. So it's 1, 2, 3, 4, 5. 5 is the exponent. Okay, so this is 7 to the 5th power. Here we have 6 times 6 times 6 times 6 times 6 times 6 times 6. So the base is obviously 6, right? That's the number that's being multiplied by itself. And then what's the exponent? what is the exponent? Let me just label this real quick as the base. The exponent, again, tells us how many factors of 6 we're going to have. 1, 2, 3, 4, 5, 6, 7. So this would be to the 7th power. This is my exponent. What about 9 times 9? Well, the base here, again, is the number that's multiplied by itself, and that's 9. So this is my base. And the exponent tells me how many factors I have. So I have 1, 2 of those. So the exponent is 2. This is my exponent. Very, very easy. What about 4 times 4 times 4? Again, my base is going to be the number that's multiplying by itself. So that's going to be 4. And then my exponent tells me how many factors I have. So I have 1, 2, 3. So 3 is my exponent. Okay, so I have here that we also need to be able to reverse this process. So what does that mean? Well, basically what I'm saying is that when you see a problem with exponents in it, you need to be able to reverse it and write it as a repeated multiplication. So in other words, if I have 10 to the 4th power, write this using multiplication. So I know the base is 10, so that's the number that's being multiplied by itself, and the exponent is 4, telling me I have 4 factors of 10. So this is 10 times 10 times 10 times 10. Right, I just did the thing I was doing before, only backwards. Right, I took it from where it had an exponent and wrote it with multiplication, whereas before I was taking with multiplication and writing it where it had an exponent. What about 9 to the 6th power? Well, my base is 9, so that's the number I'm multiplying by itself, and 6 is the exponent, that's how many factors I'm going to have. So 9 times 9 times 9 times 9 times 9 times 9. I have 1, 2, 3, 4, 5, 6. 6 factors of 9. What about 12 to the 10th power? Well, I'm going to have 10 factors of 12, right? My base is 12. Again, that's the number that's being multiplied by itself. And 10 is the exponent. It tells me how many of them I have. So this is 12 times 12 times 12 times 12 times 12 times 12 times 12. And I lost count. How many is that? 1, 2, 3, 4, 5, 6, 7. So I need 3 more. So times 12 times 12 times 12. So now we have 10 factors of 12. Then the last one we'll look at is 5 cubed. Or again, you could say 5 to the 3rd power or 5 to the power of 3. Doesn't matter as long as you know that this is 3 factors of 5. Right? The exponent is a 3 and the base is 5. So that means I have 5 times 5 times 5. Okay, so the next thing you need to be able to do is evaluate when you see an exponent. So if I see something like 2 to the 7th power, and your teacher says, what's the value for that? Or what's it equal to? Well, the first thing I'm going to do is I'm going to write this using multiplication. So in other words, I have 2 as my base, and I have 7 factors of 2. So just exactly what we just did. So 2 times 2 times 2 times 2 times 2 times 2 times 2. So 7 factors of 2. And then I just go through and multiply. And a lot of times, especially for these scenarios that come up often, you'll just memorize what the answers are. I already know that 2 to the 7th is 128. I don't even need to do the multiplication. But we're going to go through and say 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, 64 times 2 is 128. 128. What about 3 to the 4th power? Well, again, we're going to write this using multiplication and then just do the multiplication. So 3 to the 4th power is 3 times 3 times 3 times 3. Again, 4 factors of 3. The 4 is the exponent, tells me how many factors I have. 3 is the base, that's the number I'm multiplying by itself. So 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. 81. What about 17 squared, or 17 to the power of 2? Well, this is 17 times 17. And I don't know this off the top of my head. I would have to either use a calculator or do vertical multiplication. So let's just do that on the screen here. So 7 times 7 is 49. 7 times 1 is 7, plus 4 is 11. And now the benefit of this is I'm multiplying 1 times 17. So that's easy to do, right? I just shift this over here, and I can just basically write 17 as my answer, and now I can just add. Bring this down. 1 plus 7 is 8. 1 plus 1 is 2. So we end up with 289, and so we'll write this is equal to 289. Okay, what about 15 squared? Well, again, we would write this as 15 times 15, and then we would multiply. So I happen to know 15 times 15 off the top of my head, but in case you don't, you would do a vertical multiplication. This is 225, and this is one that's going to come up quite a bit. Okay, what about 4 to the 5th power? So this is 4 times 4 times 4 times 4 times 4. So this one's pretty easy to do in your head. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. And then 256 times 4 is 1024. And again, this is another one that I have memorized. We'll learn later on that 4 to the 5th power is the same as 2 to the 10th power. And I know that probably doesn't make any sense to you right now, but later on you're going to understand why that's the case. So the answer for right now, though, is, again, 4 times 4 times 4 times 4 times 4, which gives us 1024. Okay, lastly, let's talk about 10 raised to a whole number larger than 0. This right here, what I'm going to teach you, is going to save you a lot of time because you come across these problems a lot, and there's a very simple way to solve them. So let's say I have something like 10 to the 2nd power. What's that equal to? Well, it's 10 times 10. Now, I taught you in the lesson where we talked about multiplying with trailing zeros, you can do 1 times 1 and then attach 2 zeros to this. So this is 100. Notice how 10 squared produced 2 trailing zeros. This is 2 trailing zeros. Look at 10 cubed. This equals 10 times 10 times 10. 1 times 1 times 1 is 1. 3 trailing zeros. 1, 2, 3. So 3 as the exponent, 3 trailing zeros. And I think some of you can already see where I'm going with this. If I have 10 to the 4th power, 10 to the 4th power, I get 10 times 10 times 10 times 10 equals 1 times 1 times 1 times 1, which is 1. And then 1, 2, 3, 4 trailing zeros. 1, 2, 3, 4. So again, the exponent is 4, and I have 4 trailing zeros. So here's the rule. If we're working with whole numbers and they're larger than the number 1, so meaning 2 and moving out forward, okay? I didn't include 1 in that because 10 to the 1st power is just 10, and we learned that earlier. But essentially what you do is you write a 1 followed by the exponent number of zeros. That's it. It's very, very simple. So this is especially helpful when we have some huge number. Let's say we have something like 10 to the 11th power. I could go through and write out, okay, 10 times 10 times 10, basically 11 factors of 10. You could go through and multiply them. I'd be there all day if I didn't use the trick for trailing zeros. Using this trick with exponents, it's very, very simple. I write a 1 and I follow it with 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Comma, comma, comma. So I end up with 100 billion. And go ahead and punch that up on a calculator. You see that it's correct. And again, this works. So you could do something like 10 to the 15th. That would be a 1 followed by 15 zeros. Or 10 to the 90th. That would be a 1 followed by 90 zeros. So using this technique can help you out a lot, because a lot of times on your test, you'll get at least 1 to 2 of these where they'll say, okay, what is 10 to the 4th? Or what is 10 to the 7th? And you just write a 1 and you follow it with 4 zeros. Or with 10 to the 7th, you write a 1 and you follow it with 7 zeros and you're done. Right? You don't have to sit there and go through and multiply and do all this extra work. Hello and welcome to Pre-Algebra Lesson 16. And in this video, we're going to learn about the order of operations. So the lesson objective for today would be to learn how to solve problems with multiple operations involved. Okay, so up to this point, we haven't really discussed any general rules for solving a problem with multiple operations in it. This is what the order of operations is going to do for us. The order of operations tells us which operation to perform in which order when we're faced with a problem that contains multiple operations. So I'm going to read through the order of operations and then we're going to work a bunch of problems. So kind of the first step, or you would say your highest priority when you're working a problem, would be to work inside of any grouping symbols. And then I have a side note here. If multiple grouping symbols are present, you start with the innermost set and work outward. Okay, then the second step, or your second highest priority, would be to perform all exponent operations. Okay, so anything that involves an exponent, you need to do that second. Then third, or your third highest priority, is multiplication and division. Now, a lot of students get confused with this. You want to multiply or divide working left to right. So multiplication does not come before division. Division does not come before multiplication. They are on the same level. You do them from left to right. So if I had something like 4 times 5 divided by 2, I would multiply first. So I would do 4 times 5 first, and then I would take that result, which is 20, and I would divide by 2. So this would be 20 divided by 2, which would give us 10. Okay? Now, if I kind of flip the order around, let's say we use some different numbers here. Let's say I had 10 divided by 2 times 3. In this case, division occurs to the left of multiplication, so we would now divide first. 10 divided by 2 is 5, and then we would multiply by 3, giving us 15. So you can see that multiplication and division, again, it's on the same level, it's the same step. We do it working left to right. Okay, then your lowest priority, your fourth priority, is addition and subtraction. So I have here add or subtract, again, working from left to right. So addition and subtraction occur on the same level, just as we saw with multiplication and division. So if you have something like 4 plus 3 minus 1, you would add 4 plus 3 first. 4 plus 3 is 7, and then you would subtract away 1. If I was to switch this around and put a subtraction sign here, an addition sign here, you would now subtract first, right? Because subtraction is to the left of addition. 4 minus 3 is 1, then 1 plus 1 is 2. Okay, so we're going to start looking at some problems here. And really there's not much to the order of operations other than memorizing what's the priorities. 1, 2, 3, 4. And a lot of students will use kind of some clever tricks to remember it. I know that one of them when I was in high school was, please excuse my dear Aunt Sally, right? And you'll hear this all the time. You'll hear PEMDAS, PEMDAS. But you have to be careful with stuff like this. This is please excuse my dear Aunt Sally. You have to be careful with this because this is basically parentheses, exponents, multiplication, division, addition, subtraction. Remember, these two occur on the same level, and then these two occur on the same level. You have to remember for this step, it's left to right. And I can't stress this enough because I have a lot of students that kind of mess this up because they use things like this and they say, well, no, multiplication comes before division, PEMDAS. Multiplication, division, left to right, left to right. Addition, subtraction, again, left to right, left to right. So if you can't remember that, please take out a pen and a piece of paper, write that down. Multiplication and division are on the same level. We perform them left to right. Addition and subtraction on the same level. We perform them left to right. Okay, now having said that, let's start on our first problem. And we want to just evaluate each, which means we're just going to find the value. So when we look at 4 minus 3 plus 5, that's our first problem. We have two operations here. We have a subtraction operation and we have an addition operation. So which one are we going to do first? Again, addition and subtraction occur on the same level. So we're going to work left to right. So I start at the left part of the problem and I go to the right. So 4 minus 3 will be done first, and 4 minus 3 is 1. So I'm going to replace this part right here, this operation, with a 1. And then I'm going to write the rest of the problem. So then plus 5. And then 1 plus 5, I do that. That's 6. Very, very simple. Next, we have 5 times 2 minus 1. So our operations here, we have multiplication and we have subtraction. So multiplication has a higher priority. We need to do that first. So I'm going to do 5 times 2 first. So what is 5 times 2? Let me just highlight this. 5 times 2 is 10. So I'm going to replace this part right here, this operation, with a 10. I'm going to put a 10 there, and then I'm just going to copy what remains. So then I have minus 1. Minus 1. And now I'm free to perform that operation. 10 minus 1 is 9. Okay, for the next one, we have 4 squared minus 3. And if we look at what we have here, we have an exponent involved, and then we have subtraction. So the exponent has the highest priority, and so we would evaluate 4 squared first. 4 squared means that I have 2 factors of 4. So 4 times 4, that is 16. So I'm going to replace this with 16. And then we copy what's left from the problem. It's just minus 3. Minus 3. So 16 minus 3 would give me 13. Okay, so now we're going to make them a little bit harder. Up to now, we've only seen things with kind of 2 operations involved. Now we're going to kind of get into 3, 4, 5, and more operations involved in one problem. So we start out with the quantity 2 plus 1. And again, I say the quantity because 2 plus 1 is inside of a set of parentheses. Then we multiply by 3, then we multiply by 2. Now, the highest priority in any problem is always what's inside of the parentheses. So I would perform this operation before anything else. And where students get confused is they say, oh no, you have addition here. Well, it doesn't matter, because when you have parentheses, you must work inside of them first. So we're going to do this first. So what is 2 plus 1? 2 plus 1 is 3. So I'm going to write that over here. I'm basically just replacing this with a 3. And then I copy the rest of the problem. I have times 3 times 2. So I'm just going to work this left to right. 3 times 3 is 9. And then 9 times 2 is 18. So this would be a final answer of 18. Okay, now we have 6 plus 8 divided by the quantity 5 minus 1. Again, we have this quantity here, 5 minus 1, because it's inside of parentheses, right? The 5 minus 1 is inside of parentheses. So we perform whatever operation is inside of parentheses first. So 5 minus 1 is 4. So I'm just going to replace this with a 4 and copy the rest of the problem. So 6 plus 8 divided by, and again, the result of this is 4. So now if we look, we have addition and we have division. So division is a higher priority. Okay, we want to divide before we add. So that means I'm going to do this problem first, which is 8 divided by 4. So 8 divided by 4 is 2. So again, this right here will be replaced with a 2. So I'll have 6 plus 2. 6 plus 2. And to finish this off, 6 plus 2 is 8. Okay, for the next problem, we have the quantity 1 plus 1 divided by, and then look inside of parentheses here, we have something that's a little bit longer than what we're used to. We have 6 minus 2 times 2. So we have 2 sets of parentheses here. Now here's what really matters. You need to make sure that you perform the operations inside of the parentheses separately from this division. Okay? So in other words, you'll get some result here, and you'll get some result here, and then you're going to perform your division, not before. Okay? That's what those grouping symbols are there for. So let's start out with the set of parentheses on the left. We're going to do 1 plus 1. We all know 1 plus 1 is 2. So we're going to replace this with a 2, and then divided by, and then inside of parentheses, we have 6 minus 2 times 2. So we're not doing any division yet. We're still working inside of parentheses. Still working inside of parentheses. Now, once you get inside of a set of parentheses, you might have a decision to make. You see how you have subtraction here and you have multiplication. You have to reapply your order of operations. Multiplication occurs before subtraction. It's a higher priority. So we would do 2 times 2 first. Okay, so 2 times 2 we know is 4. So let me just circle this guy. This right here is going to be replaced with a 4. Okay, so equals 2 divided by, and inside of parentheses I'm going to have 6 minus, and the result of this again was 4. And we're still continuing inside of the parentheses, even though we just have one operation left. We want to do 6 minus 4, and that's 2. So we're going to have 2 divided by 2, right, because the result of this is 2. And then we finish this problem up by performing the division. 2 divided by 2 is 1. Okay, for the next one, we have the quantity 14 minus 2, then divided by, and here we have a 2 next to a set of parentheses. So again, that implies multiplication. So 2 times the quantity 5 plus 1. So we know we're going to start out by doing the operations inside of parentheses first before we do anything else. So we're going to start with 14 minus 2. 14 minus 2 is 12. So I'm going to replace this with a 12. Okay, and I just copied the rest of the problem. Next, we're going to work inside of this set of parentheses here. 5 plus 1 is 6. So I'm going to say this is 12 divided by 2. Then remember, this implied multiplication. So this will now be times 6. Okay? Just because we didn't have a multiplication symbol there, again, you have to remember that as we move higher in math, when you see a number next to a set of parentheses, again, it implies multiplication. So this is our problem now. We have 12 divided by 2 times 6. Remember, if we have division and multiplication, they occur on the same step. So we're going to work them left to right. So that means I'm going to divide 12 by 2 first and then multiply by 6. So 12 divided by 2 is 6, and then times 6. So then 6 times 6 is just 36, and that gives us our final answer. Okay, let's take a look at one final problem. So we have 6 squared minus, and then we have the quantity 2 plus 3 minus, and then we have another quantity 3 plus 13, and then finally divided by 4. So again, the highest priority you're going to face in any problem is always going to be what's inside of parentheses. So we have parentheses here, we have parentheses here, and let's figure out what 2 plus 3 is first. So I'm going to rewrite this part, 6 squared minus 2 plus 3 is 5, so I'm just going to replace this with a 5. And then minus, we have this inside of parentheses, 3 plus 13, and then divided by 4. Now, the next step is to work inside of these parentheses. We're going to do 3 plus 13. So we're going to have 6 squared minus 5 minus, so what is 3 plus 13? That's 16. That's, again, 16. And then divided by 4. Okay, so now when we look at this problem, I have an exponent, I have subtraction, more subtraction, and division. So the exponent is what we're going to deal with first. That's the highest priority. 6 squared is 2 factors of 6, or 6 times 6, which is 36. So again, I just replace this with a 36, and I can copy the rest of the problem. So I have minus 5 minus 16 divided by 4. Now I have subtraction, more subtraction, and division. Division has the highest priority. So we would do 16 divided by 4 before we do anything else. 16 divided by 4 is 4. So I'd have 36 minus 5 minus, and again, this operation right here resulted in 4. And now I have just straight subtraction, so I'm going to work left to right. 36 minus 5 is 31, so that's 31 right here. And then we have minus 4. And then lastly, 31 minus 4 is 27, and that is our final answer.